A very good morning to all of you. Today is the fifth day for this GIAN course on Industrial and Vehicular Aerodynamics. Today we have Professor Arnab of Aerospace Engineering Department at IIT Kharagpur. Let me introduce Professor Arnab to all the participants who are attending this course. Professor Arnab did his bachelor's in mechanical engineering from Jadavpur University, then master's degree from IIT Madras and PhD from IIT Kharagpur. He has a long experience working in various industries and academia in this country and abroad. Professor Roy's expertise lies in both computational as well as experimental fluid dynamics and aerospace propulsion. He is currently working in some of the areas including block body aerodynamics, fixed and flapping wing aerodynamics, shock wave boundary layer interaction and interacting cavitation bubbles. Professor Roy is a visiting researcher of various laboratories in Europe like Aachen University, Technical University Stuttgart, Technical University Brunswick. So let's welcome Professor Roy.
Thank you, Professor Akshoy, Ranjan, for the nice introduction. I'm really glad and grateful to the authorities of Motilal Nerhu National Institute of Technology, MNNIT Allahabad, especially the GIAN Program team, including Dr. Abhishek Kundu, Dr. Akshoy and Professor G.P. Sahu for having invited and included me in this very interesting GIAN course, Industrial and Vehicle Aerodynamics, a new frontier for India's economic prosperity and energy security and a sustainable environment. So it has been supported by Ministry of Education, Government of India and hosted by MNNIT. Professor Firoz from RMIT Australia. He is the foreign expert for this course and his presence has been very important for making this course more meaningful. Professor Shubhankar Sen from IIT ISM Dhanbad has contributed to this GIAN course. He gave us a very interesting lecture yesterday on application of computational fluid dynamics on block body flows. I am also here as one of the Indian experts and I would like to talk briefly about computational aspects of block body flows and a little bit of vehicle aerodynamics today. And it's so nice to see a lot of young faces here in the audience, and the course is intended for them. They are the torch bearers of activities of this kind, and I think they will take the whole purpose of this course forward in trying to implement things that we are trying to discuss today. With this, let me move on to the contents of the course of my presentation. So since I'll be talking mostly on computational fluid dynamics applications, a very brief, if you say, definition in my own words, where we talk about computational fluid dynamics as analysis of systems involving fluid flow, heat transfer and associated transport phenomena, which could also include things like chemical reactions, for example, based on computer based simulations. And what do we do in order to perform CFD? We solve a system of governing partial differential equations and we have to solve them approximately using suitable initial and boundary conditions. Most often we do not have analytical solutions available for such equations. They are usually complex coupled partial differential equations like what Professor Shen was talking about yesterday. And usually if you look at the steps broadly what we follow in performing CFD simulations of a flow problem, it includes problem definition and objectives of performing the CFD simulation. For example, from the perspective of this course, it could be solving flow past a vehicle or solving flow past a ground based structure like a building or a chimney, a tower, things like that, or say a wind turbine. So you can look at an object of interest and then try to define what exactly you would like to solve around that object or through that object. So we talk about external aerodynamics, internal aerodynamics and so on, and then you choose a set of suitable equations which are appropriate to solve the kind of problem that you are looking at, and proceed with the approximation as we said. So choice of governing equations is very important because that defines the kind of physics you can capture. That also defines the level of approximation to reality that you can actually achieve. And therefore, if you are solving an inviscid flow, whether it's incompressible or compressible, incompressible and compressible has been discussed about by Professor Firoz in another lecture. So you remember about the density change and its coupling with pressure. So if you are looking at such problems, you solve Euler equations where you are basically looking at an inviscid flow. It's devoid of viscosity, right? But very often you see in vehicle flows, there's a lot of flow separation and so on. What Professor Alam was showing us, very interesting flow visualization, etc. What Professor Shen was talking about, that formation of wake behind a bluff body. So that's very much dominated by viscous effects, right? So in that case, most often we'll end up solving Navier-Stokes equation, and for the kind of flow regimes that we talk about in vehicles of this kind, we may end up solving incompressible Navier-Stokes equations most often. When you look at more high speed vehicles, then you talk about compressible Navier-Stokes equation solution most regularly for aircrafts and things like that, especially say the passenger or transport aircrafts, the kind of Mach numbers that they fly at, etc. That makes it necessary to solve for the compressible form of the equations. So after you make these choices, and these choices have to be well informed, you have to have the necessary knowledge, the background to make these choices. That's very important. Then you go into the core steps of CFD. So you talk about defining a domain for solving the problem. So when you look at a moving car on the road, if you look around it, there's a very large region around that car, virtually an infinite region, on surrounding it. So if we think about computing so much around that car, we will end up running out of computing power. So we try to confine the region over which we will try to solve the flow around the car, and therefore there comes up this domain definition. And once we define how much region around the car we are going to confine our study to, that is, the domain dimensions are defined, then we think about discretizing that domain. That means breaking it down into bits and pieces so that we can solve those governing equations approximately at a set of points or over a set of control volumes and things like that. So that is what we are talking about, the discretization process. So mainly this is categorized as a pre-processing step, in the sense that before we start the computations using the solver, the equations are being solved, you have to make this preparation before that solution starts. Then you go into the flow solver step, which is basically the heart of the whole activity. So you are going to solve those governing partial differential equations, and based on appropriate initial and boundary conditions, you have to make a well-informed choice about the kind of discretization approach you are going to follow. So you basically convert the partial differential equations to a system of algebraic equations. Most often we end up doing that. and you may look at different techniques like finite difference technique or finite volume or finite element method. Finite element Professor Shen was talking about yesterday. Well, I'll mostly talk about finite difference very briefly, and then once you have got them converted into a set of algebraic equations, then you start solving them. Of course, the computer gets very intensely engaged into that activity, and this may be a very time consuming activity if you have a large number of points at which you need to solve the problem, and this is usually called as the flow solver step. Finally, once you are done with the solution of the governing equations, you will end up having thousands and hundreds of thousands or millions of data, and you need to store them suitably. You also need to handle them suitably with some post-processing softwares. Okay, so softwares which can handle this enormous amount of numerical data and then help analyze the data and give you results which can help you what exactly happened when the flow took place around that vehicle. So that is basically the post-processing step that we are talking about. If you were to ask this question, that what are the advantages of carrying out a CFD simulation, because we were looking at a lot of experiments during the last few days, and there's absolutely no alternative to performing physical experiments in wind tunnels, but CFD also plays a big role here in the design of the vehicle. So we need to really understand where the advantage lies. If you look at the bullet points, you see that we can have high resolution numerical data in space and time. That's the first point, and this is the first point. So space and time, in the sense that space, we said that we have a domain over which we are solving. It's a physical domain. It contains that car or the vehicle somewhere inside, all right, and there are a lot of points or control volumes surrounding that object of interest. So that domain is split into a large number of points which are very nearby, very close by, and therefore based on how close they are, you can actually have a resolution in space. So the closer they get, you have a better resolution. The shorter the time step over which the computation progresses over time, the better is your time resolution. So these are things you can choose, but if you choose to make it really fine in terms of spatial discretization and also in terms of time discretization, it gets increasingly more expensive. It takes a lot of time to run the simulation. So sometimes we have to make a very rational choice, that how fine do we need it? Do we need it really that fine, or we can compromise with lesser number of points in space or larger time intervals? And then of course the flow parameters can be changed rather easily. In fact, boundary conditions can also be changed rather easily. We can suddenly set a wall, a solid wall, into a fluid wall. Okay, so those things are not so easy to do in an experiment, because we have to find ways of modifying the test section, then remove a wall physically and bring about that change. But here it's comparatively easier. Okay, then there may be constraints in terms of test section size, test section velocity, or choice of working medium, like Professor Alam was very nicely explaining to us, because we have to make compromises and so on. Here generally we have a little more liberty in terms of exploring the parametric domain. Then comes the probe. You can probe virtually anywhere in the flow field, because the probing basically is based on where you have located those points, where you have located those control volumes, and you have the data available at those regions. And those points, maybe some of them could be difficult to access in experiments. Then comes the issue of doing all this probing non-intrusively. So you do not put in a probe to make the measurements here. So any probe of any dimensional extent will to some extent disturb the flow in its neighborhood. It's a source of perturbation for the flow. So that doesn't arise here. So you are not going to do it intrusively, so you are not going to disturb the flow, but still probe the flow. Then comes perform extensive parametric studies, maybe over a wide parametric domain, wider than what you can manage in experiments quite often. And you can also make use of parallelization in your algorithm so that you can distribute your computing load across several processors and make it quicker. And when you need to design a particular model, you may end up needing a lot of computer simulations to gradually optimize the design. So repeating the simulations with modified geometry to accommodate design changes may not be so very involved. You just need to talk about changing the CAD model, and then basically the boundaries, the boundary conditions that you impose, all can be left untouched, and you can go ahead with successive simulations with less effort. Now where comes the disadvantages or the limitations? There are quite a few. One of the limitations which you learnt about yesterday through Professor Shen's lecture was you never know whether you are getting the physics right. So when you are solving flow past a cylinder, if you are not knowing a priori that the flow remains two-dimensional up to what range of Reynolds number and three-dimensional beyond, and you just blindly keep running two-dimensional simulations, then where do you lose out? You lose out in ranges where it actually turns three-dimensional. The solver will never complain, it will churn out results for you, but you won't know where you have gone wrong, and therefore any design that you base on that would go wrong beyond a certain point altogether. Now unfortunately the CFD tools are not so intelligent that they will point out this anomaly to you. They will just churn out the numbers for you. So you need to be well informed, knowledgeable enough to understand where it may falter. Therefore prior knowledge of the physics is essential. At least you need to be very careful about some of the issues which may take you by surprise. Again, you may say that then in order to be on the safer side, why don't we run all simulation in 3D mode? You cannot, because those are extremely expensive. Therefore you need to have the necessary knowledge to switch over to 3D whenever it's required. So that's like an example that Professor Shen pointed out to you, and that's one of the examples that we can actually cite for the first point here. I have given other examples. So if you are looking for viscous flow and you are using Euler equations, it will be faulty. If you are solving boundary layer equations to solve a largely separated flow over a blob body, it doesn't work, because boundary layer by definition falls in the category of attached flow, right? Ran's equations, some of you may be aware of this, that when we solve turbulent flows, there are different ways of capturing the turbulence. So we may or may not end up using models to capture it. So when we don't use any models whatsoever, we directly solve the equations, then we essentially solve it by the direct numerical simulation approach, right? But that is usually very expensive, especially when the Reynolds number goes up, right? Because as you know that there is a widening scale separation between the largest and the smallest eddies, and therefore in order to capture the smallest ones, your grid has to become finer and finer, and therefore a lot of grid points or a lot of grid volumes, and that's what will make it very expensive. Additionally, you will have to use very high accuracy numerical discretization, higher order schemes as we say. Those are also more costly to compute compared to lower order schemes. So that's how the cost escalates. While if you model a bit of the turbulence, it may make it cheaper, you may get the results earlier, but then you may end up missing some of the turbulence details. So if you model a little bit by using so-called spatial filters, we have what is called as large eddy simulation. Okay, so Professor Alam was talking about a lot of unsteady pressure, and then if you want to capture such thing, RANS doesn't work. You have to think about at least large eddy simulation, if not direct numerical simulation. Okay, so RANS is also not good in capturing unsteady effects, and therefore it would not be reliable in capturing effects like unsteady pressure or those which are related to large scale flow separation. Therefore, the remedy is to validate numerical data with reliable or accurate experimental data. That means that's where you have to engage very actively with experimentation. You cannot just take a one-dimensional approach and finish it off. And as I said earlier already, that you should not end up capturing the physics in a faulty manner. So that is where your prior knowledge about the physics is very important. Second point, most CFD results are quite sensitive to spatial grid resolution and time step size. So how small your grid sizes are, how short is your time step, etc., will have an impact on the results that you generate. Therefore, you need to have some kind of a convergence study done in those two terms, so that you are kind of sure that with the kind of grid that you have used, with the kind of time stepping that you are using, you are going to meaningfully capture the dynamics of the flow. Third point, idealized geometry and boundary conditions which may differ from experimental conditions. So, for example, the CAD model of a car that we use in CFD usually will have smooth surfaces, absolutely smooth surfaces, while a manufactured model will always have surface roughness to a greater or lesser extent. You cannot avoid that, because there are machining processes involved, there are painting processes involved, and so on. Even if you polish it to the highest levels, that will not exactly match with the exact smooth geometries that you end up using in CFD. What will be the impact of that? How does it affect the state of the boundary layer, for example, as it flows on that surface? A perfectly smooth surface and a slightly rough surface, there may be changes of the state of the boundary layer. You never know, and neither do we know. So as future aerodynamicists, CFD specialists, you may have to think in these directions. How do we have simple models to incorporate these effects? Then when you mount a car model on the wind tunnel floor, for example, how rough is that floor? Is the floor moving? If it is moving, is the belt vibrating? What impact will it have on the aerodynamics? So the probes, whether it's microphone measurements or pressure transducer measurements, their readings, how will they conform with your CFD readings if your CFD is very idealized? Because CFD will not find a way to capture these effects. Under the wind loads, the car may be vibrating a little bit. Will CFD capture that? No, no chance. So CFD will also miss that. So these are reasons behind the gap between an ideal environment like we are trying to do in CFD and a real environment which the experiment does. Professor Alam was talking about lack of data about the atmospheric boundary layer in the first few meters within which most of our vehicles are immersed. There is uncertainty about the wind speeds and things like that. Would we be able to meaningfully simulate such effects in our CFD? I am very doubtful. We will again idealize there. Probably we will put a shear velocity profile or something like that, which is again idealized, but which will not match exactly with the road conditions. So there are differences. Inability to account for spatial temporal variations of flow properties through the imposed boundary conditions. That's what we were talking about. So there are limitations. Let's accept that, and with that we proceed to the three main steps. As I said earlier, that we talk about domain definition and discretization, the grid generation step, which is the pre-processing step, and depending on the kind of body boundary that you choose to solve your flow around, you have to look at how to wrap a nice mesh around that geometry. That mesh should be really nice. Okay, and from some of the examples that you see here, right on the left, is a very simple example. This is what we generally start off in classroom discussions, right? You have a flat plate and you want a rectangular domain to be formed around the plate. The plate is at the bottom, and if you imagine that there is some flow coming from the left, then there will be a boundary layer formation on the plate, right? That's a very classical problem we talk about. In order to capture the boundary layer, notice that the grid is very fine over here. Why is it? Because within the boundary layer there will be very rapid changes of the velocity from a zero velocity at the wall, which is the no slip condition for viscous flows, to the free stream velocity, right? And that happens over a small thickness. We know that the boundary layer thickness is very small compared to the characteristic dimension, which could be the length of this plate, for example. So within that very short length that we are talking about, you have to have a large number of grid points placed so that you can capture the variation in a detailed manner. Why does that matter? Because based on that, you will be able to predict your skin friction or shear stress on this wall. The other day Professor Alam gave you the expression for shear stress. It depends on the viscosity coefficient and the velocity gradient. It's a combined effect of the two, and the gradients are very high over here, and that's where the shear stress will become active and will act on the wall. So if you don't capture the gradient properly, the shear stress will be wrongly predicted, and therefore you will get a very wrong impression about what frictional drag this plate will face when it is exposed to that flow. Now the same effect will work on other geometries also. On a vehicular geometry also such things will happen. So you need to have a very fine mesh wrapped around the surface so that you can actually capture the near wall variations with a lot of accuracy, because that has a very close connection with good prediction of the skin friction, and that affects the drag value which you will end up getting. Okay, so different kinds of geometries may need to be handled, based on which we say that you may need to use structured mesh, or you may need to use hybrid mesh, which is basically a combination of structured and unstructured mesh. And I think you all are smart enough to understand what is structured and unstructured if you look at the topology of the mesh, right? So this looks nicely ordered, a family of lines moving normal to the body, another family which are tangential, while the unstructured is a kind of randomized. All right. So here, because we are talking about a planar situation, you see triangular cells when it is the unstructured part, and you see quadrilateral cells in the structured part. If you talk about a vehicular body, you would need to actually have a three-dimensional mesh, right? You have a three-dimensional mesh wrapping around that body. So it's a complex body, so most often you may actually end up doing this, hybridizing structured and unstructured, or sometimes using several blocks of the structure instead of using a single block, so that you can cater to the complex geometries. For example, if you have a mirror protruding out of the main body, you may not be able to capture that surface very nicely, neatly, if you use a single block to wrap on the main body as well as the mirror. So you may need different blocks to capture different geometries with accuracy. All right. So those are the tricks that we talk about over here. I'm not going into all this mathematical part, because you just need to see the bigger picture, and you all are smart enough to do the rest. Now comes that Ahmed body Professor Alam was talking about yesterday, and you see a typical mesh around it. So again, around the Ahmed body, you see in the neighborhood, the mesh has been refined to a great extent, and then it is coarsened out as you move away. Why don't you need it to be so fine all around when you are far away from the body or far away from the road surface? It's just because the velocity gradients are going to be trivially small over there, and therefore even if you have a coarse mesh, you will not commit a lot of error in computing it, while the gradients would be much larger here. And again, it has an influence on skin friction, it has influence on the drag. Consequently, the pressure distribution predictions may not be all that good. You may not be able to capture the features of the wake behind the body very well, and so on. That's why you have such a refined mesh over here. So what have you prepared? You have prepared a digital representation of the vehicle geometry using a specialized CAD software in order to create that envelope around which you are going to wrap that mesh, and that CAD model should capture all the external shapes, the dimensions of the components like mirrors, spoilers, protrusions, air vents, rooftop add-ons. We were seeing pictures of all those, So all that should be incorporated in the CAD model. Then comes the mesh generation, and mesh again can be generated by different means. It also needs to be coupled with the solver. So when you generate the mesh, you also have a lot of mesh information to store. The format in which you store the mesh information will have to be compatible with the kind of solver that you use. Alright, so if you are using finite difference method, you end up solving the partial differential equations in their differential form, which are applicable at points. And then you are solving the grid point information. Where is that grid point located? Can I locate it using indices I, J, K, or I just have the locational information and then the information about the neighboring grid points. That may be all that I need for a finite difference calculation. But when it comes to finite volume calculations, first of all, your partial differential equations would have to be in the so-called integral form. All right. So you have a set of integral equations solved on control volumes. The control volumes may look like quadrilaterals or triangles in 2D in planar space. In 3D, the quadrilaterals will become hexahedrals, the triangles will become tetrahedrals, and so on. Therefore, you have some kind of polygonal structures, right? And they have surfaces, they have faces, and there's going to be movement of mass and momentum across those faces. So you solve all that in an integral sense through flux movements. And then if you are handling a finite volume technique, what kind of grid information do you need? You need to know which are the grid points which form the corners of that control volume. Okay, so for a quadrilateral control volume, you may have 4 corners. So you may have numbers of those nodes, you may have coordinates of those nodes, you may have to have information about the neighboring cells which share common faces with that control volume, and so on. Alright, so the grid information, how you store it, is very important, because that's what the solver is going to access next, and it has to be compatible. Alright, so that way we have to track the mesh generation as well as storage of information once the mesh is generated. Okay, and then of course you have to check the quality and resolution of the mesh, which is very important in order that you get meaningful results out of it when you solve the equations. What if instead of a vehicle like an MNNIT body, you had a building to solve the flow around? Because here we are also talking about industrial aerodynamics, wind engineering kind of problems. So you have a earth fixed structure and you have a mesh formed around it. So the mesh that you have formed over here, the upper variant is a structured mesh that you have formed. From your earlier exposure to structured mesh on a curved surface, you can clearly figure out that this is also a structured mesh. This looks more like that flat plate thing, but now on the flat plate you have a building sitting out there. And the moment the building sits out there, you have to probably refine the mesh in a much better way around the building. But look at the thing, that once you have a structured mesh, if you refine here, that refinement goes on top all the way. If you refine on top, that goes on upstream and downstream. If you refine around the building, it also goes upstream, downstream. Well, that may not be a bad idea, because that's a solid surface after all. You may not like to have details over there, but this may be a kind of wastage. Therefore, a smarter way of doing this grid could have been break it down into blocks and refine the blocks that you need and coarsen up the blocks which you don't need to that extent. And then you have a so-called multi-block structured grid, which in terms of grid numbers will reduce your computational expenses. At the same time, you will have the desired grid resolution around the main object of interest. So these are the things you have to think over when you plan a numerical simulation. Alright, based on the available computational resources, etc., such planning has to be done. Again, remember that this is just a planar projection that we are looking at. The building is actually a 3-dimensional surface, right? Therefore, you are wrapping a 3-dimensional grid around it. So if you say that this is X and Y, then there is also a Z coming out of the plane of the slide. So you will also have to have the grid extruded in that direction, and the body will sit somewhere in the middle on the surface of the earth that you are trying to model at the bottom. And then comes the issues of what conditions do you impose on the boundaries and things like that, which we will come to later. Another way of generating the mesh is this, which is completely unstructured. Only difficulty with a completely unstructured mesh is maintaining the formal order of accuracy. Okay, so with the same level of refinement, there are theoretical means by which we can show that usually the accuracy degrades a little bit if we have an unstructured mesh compared to a structured one. That's why we generally prefer doing a structured layer at least surrounding the immediate neighborhood of the building, followed by an unstructured far field, which will always be better from the accuracy point of view. Again, here I have mentioned that, you know, if it is a 2D problem, you will have rectangular mesh. If it is extruded in the third direction, it will give you a hexahedral mesh. And if it is a structured mesh, additionally we can associate mesh indices. Each one of these mesh points can be given indices. So in 2D you will have a I comma j index. I gives how many levels of grid points have you crossed to reach that point along the x axis. The j gives how many grid points have you crossed along the y direction to reach that point. And again in the third direction it would get a k index. Alright, and in this way monitoring the information in a structured grid becomes so much more easier. Also writing the solver becomes easier, while things are more complicated here. Handling the grid information itself is a big challenge here, and then interfacing it with the solver is also equally challenging, and therefore it's a little more difficult to handle things here. In 2D plane you will have triangular cells that you can see over here. It's not necessary that you always use triangular cells. You can have mix of triangles and quadrilaterals or even pentagons or hexagons if you want. But the main thing is you have to look at the regularity in which you have a system of two families of lines intersecting to define a point, which goes missing over here. It gets randomized completely. But the advantage is you can refine very selectively in regions that you want and very easily coarsen it out in others. In unstructured mesh, this indexing goes missing. You cannot implement it. Wind loading on the building would be accurately predicted or calculated if you use a well refined mesh around it, as well as in the wake. And let's say if the wind creates very large loads on the building, or the building is a very tall one, like Professor Alam was mentioning about a 1 meter deflection on the top floor of a building. So in that case the building may be actually swinging, and therefore having a fixed mesh around it it's not going to give you accurate predictions, because the building is moving. You cannot fit the mesh points forcibly at a particular spatial location and say that the building will remain there, because the building will actually not remain there under the wind loading. So what do? You have to make the mesh follow the building, and there comes the issue of deforming mesh. Alright, so you need to have a kind of dynamic mesh, so to say, to follow the building and conform with it. That is one way. There are other ways of doing it as well, where you have a fixed background mesh and you have a moving body in the foreground and still accommodate for the problem in some way. Okay, so you are bright young students, you just need to listen to these different directions and explore further, and I think you'll get the different approaches very soon if you read a little bit about this. So such problems would be categorized as fluid structure interaction problems. You know, there's a fluid medium interacting with the structure, making it deform or making it deflect. Alright, so once it deflects, the structure again has a different interaction with the fluid medium, right? So there is a talking going on between the fluid and the structure domains, and this continuous interaction between the two, both way interaction, would have to be modeled appropriately. Alright, so you need to have a kind of a coupled solution between what's happening in the fluid domain, what's happening in the structural domain, right? Let's come to the solver step. So here what do? We talk about method of solution of governing equations. As I said, that the kind of problems that we are talking about, most often we are going to end up solving the incompressible Navier-Stokes equations. So what are they comprised of? They are comprised of the mass conservation equation, which is called as the continuity equation, and you all know that there are ways of showing how in the incompressible domain the mass conservation equation comes to this. It's divergence of velocity vector going to 0, right? And then when you are working with the Cartesian framework, then it basically becomes a summation of those three spatial derivatives of the velocity components. Alright, so you sum them up and they go to 0. So I hope all of you are very familiar with this vector calculus operators. You can actually end up expanding this very comfortably. Here we are talking about linear momentum conservation, so it's basically Newton's law applied to your fluid. And then what does it give us? It gives us a time rate of change of the velocity vector plus the advection term, as we say. It is basically a dot product between the velocity vector and the del operator, and that applies on the velocity vector, right? Then this is basically the m into a part of the second law. All right, where is the f? F is on the other side, the forcing, as we say. The forcing comes from the gradient of pressure with a negative sign. Actually there is a density somewhere included within the pressure, and there is a 1 by Reynolds number times the Laplacian of the velocity vector. All right, so the moment you see Reynolds number, you already know that this is in a non-dimensional form. If we were to write it in dimensional form, we would not see Reynolds number, rather we would see the viscosity coefficient, right? So you should be recalling Reynolds number definition, because Professor Alam was talking about it yesterday, how to match the Reynolds numbers, right? And here comes that Reynolds number, which is so very important. So these are the two terms which are like the forcing terms, right? The pressure gradient and the viscous forces. And a very important part of solving incompressible Navier-Stokes equations is that you need to have some kind of a kind of mutual communication between the velocity and the pressure fields. Okay, left on their own, they may not be able to satisfy them. And that's why we often talk about having a pressure velocity coupling for the consistent pressure and velocity fields, which may be achieved through some kind of a pressure velocity correction technique or pressure Poisson equation solution and things like that. Usually incompressible Navier-Stokes solutions become extremely expensive because of this one single step. The most of the expense goes there, solving this equation, which usually involves a lot of iterations. So here, because you see that there is a time derivative, that means you actually would time march the solution. You are going to solve the flow from one time step to the other and to the other and so on, and you are moving the solution usually in very small time steps, so that you can resolve each and every small happening in terms of time or frequency. Therefore, you actually will be needing a time rate of change of velocity, right? That over that small time step, how much did the velocity change? So here it's a vectorial representation. If you split it apart into components, you will see the change in u, you will see the change in v, the w, which are all lowercase. The small u, small v, small w, all lowercase, would vectorially add up to this velocity vector v, is it not? So that's how we do it, between components and the vector. And we'll assume a constant density here, which in a more formal sense means that the density is kind of decoupled from pressure. Density can have a connection with temperature but not pressure, that's the thing. And these flows around buildings or car bodies and things like that would be viscous, and there's no way we can simplify them as boundary layer flows. I already told you, because there could be massive separation most often, and therefore solving Navier-Stokes equation practically becomes inevitable. Though it is computationally more expensive than boundary layer equations, you don't have a way, and therefore you need to manage with this. And then comes different aspects of the numerical approximation. Okay, so if you want to do the Navier-Stokes simulation and you have a flow solver from somewhere which is available to you, you may be able to run the flow solver somehow, but in order to run it more judiciously for your problem, you need to have some understanding of some of these things that I am talking about. On the other hand, if you are very ambitious and you have developed a solver of your own, which is very much encouraged, because that's the way you practice the things and you get to actually learn them well, just like what Professor Alam was saying the other day, that until unless you get your hands dirty, until unless you tighten the nuts and bolts yourself, you will never learn the tricks. The same goes for solver development. Okay, so it looks all so nice and fine over here in the slides, but it's a lot of hard work, a lot of failures, a lot of frustrations for months, sometimes years, for God forbid, and then you come out with some nice looking results one fine morning. That is the experience of a CFD solver developer. Alright, so it's real hard work all the way, and appreciation of a lot of nitty-gritties till you come to that point. Okay, till you can actually find out where the problems might be. And in those thousands of lines of Navier-Stokes coding, you never know whether a plus or a minus somewhere by mistake is creating havoc for you. So it could be that much meticulous an effort required to make it happen. You have to be very peaceful, very patient. You have to accept failures, and then you see a Navier-Stokes solution coming up with your own solver, which I strongly encourage you to venture into someday, if not today. Okay. Now, in order to do that, you need to have some understanding of these aspects, or maybe a little more. I have just put a few of them, and all the way through, remember that the bottom line is that decision making is involved when you make these choices. You need to develop a sound knowledge of physics and mathematical approximation to perform a good quality CFD study. Also validate your results with experiments and identify early whether you are making any major mistakes in the computations. This is very important. You need to set it firmly in your mind. And then going back to these different aspects of numerical approximation, so we already said a little bit about this discretization. Professor Shen has talked about finite elements yesterday. I briefly told you about finite difference, finite volume, at least the way we pose the governing equations, at least the way we choose the points or the control volumes, and we try to approximate the equations. Accuracy of space and time discretization, central upwind discretization, dissipative and dispersive error, explicit and implicit formulation, stability of numerical scheme. Well, life seems to be very difficult. There are so many things. Yeah, life is not easy. That's true. I'm not going to bore you with lot maths. So this is going to be not more than 5 minutes, I assure you. Okay, so a finite difference method, many of you may be aware. You all have taken ODE, PD courses somewhere in your undergraduate BTech course, and they must have taught you about all this, right? But it's just a quick recap. What do we do really with it? So as I was saying, that finite difference means we have points to work with. All right. So this point functionally may be the point x, okay, and there could be a neighboring point x plus h, where h is a small number. H may not be tending to 0 like the way we do it in calculus. Here h is small but finite. In that case, if I try to expand some kind of a function, that function could be velocity, that function could be pressure, things that you are dealing with in the Navier-Stokes equation, then how will that function behave? It will definitely behave as per this series. What series is this? It's the Taylor series. Yeah, precisely. So that's the Taylor series. Yeah, and what do we have? We have derivatives of this function somewhere, and then what is this h? H is that gap between the 2 points. I was talking about grid spacing, remember? So that h is basically the grid spacing. You have 2 neighboring points and you have decided to keep a grid spacing between those 2 points. Remember that the grid spacing may change over space. Somewhere the grid spacing is small, somewhere the grid spacing is large, because somewhere the grid is fine, somewhere the grid is coarse. So such things also have to be accommodated. But here we are not talking about that complication. We are assuming everywhere that h is going to remain the same. It's a uniform mesh, as we say. And then you have this series all written over here, and then we say that if you were to extract an expression for the first derivative of that function, this is how it will be expressed in terms of the functions at the point x and the x plus h, and the rest of the terms you may say that, oh well, those are the higher order terms, I will not look at them. Okay, so that's what we talk about as truncation error in CFD, and we want to make them small definitely, and we want to forget about them for a while so that we get an expression for f dash x, and that f dash x, if I shut my eyes to this, I have an approximation for that f dash x. Where will I need it? For example, if f dash x was del u del x in your divergence v expression, or del v del y, so that's f dash x or f dash y. Okay, so in which case fx is either u or v, as you would like to define it. So that's where you might need it. But then here the reference point was x and the other point is to the right of that point, because you have added h, right? So that's one way of defining the f dash x. It's called as the forward difference, because you have gone forward and picked a point. If you had gone backward and picked a point, you would have similarly another expression. These are like one-sided finite differences. You will later on see, if you go into books and literature on CFD, they talk about upwinding. All right, so they would say that, well, the flow is approaching from that direction, and when we look at that very difficult term of the Navier-Stokes equation, this particular term, this is what is called as the advection term, and it is a non-linear term, and we find that until unless we do one-sided finite differencing, it doesn't seem to work very well, especially when the Reynolds numbers become large. This is what people will tell you, and then they will say that, well, you need to look at the direction from which the air is approaching you, and you choose points in that direction to represent your derivatives. If you do that, then it will work. If you don't, it doesn't work. So upwinding has to do with that sense. Advection has to do with what? A movement, right? So the movement has a direction associated with it, and therefore you have to embed that directional information into the derivative. That's what we do over there. So we do one-sided differences. While there could be another way of tackling those series expressions that we wrote, and you come up with a f dash x which involves points on both sides of the reference point x. You see, one is to the right, the other is to the left. If you subtract, you go to the left. If you add, you go to the right. So you are exactly having a kind of a symmetric distribution of grid points to calculate your derivative. So this is what is called as a symmetric stencil, and they say this works fine if the Reynolds number is small. Okay, if the Reynolds number goes a little higher, you will probably have difficulty with using this first order derivative in that advection term. You may need to have a little bit of one-sided finite differencing, but with the proper direction, not the wrong direction. Okay, so this is about the first order derivative. Navier-Stokes also involves second order derivatives. If you look at the Laplacian operator, that involves second order derivatives, right? So you also need to think about the second order derivative, and just by using the two series that we have written in the other slide, just by manipulating them, you can actually get an expression for the second order derivative, which will be plugged into those viscous force terms. All right, so this is how we go about deriving expressions involving a set of grid points, and the set of grid points that we choose defines what is called as a stencil. Usually for higher order accuracy, the stencil size goes up. There are slightly advanced schemes which we call as compact schemes, where even with a reasonably small stencil we may achieve higher order accuracy, but they are a little more difficult to handle. They are all implicit schemes, and you have to actually calculate those derivatives in a kind of a so-called coupled manner by solving a system of simultaneous equations. We will not go into all that, but these schemes are explicit schemes in the sense that if you have the functional values available at those grid points, you just plug them in on the right hand side and there comes your derivative on the left, whether it is a first order or a second order derivative. Alright. While as I said, there are other schemes where these derivatives will not come up using single expressions. There will be a set of equations to solve, by means of which the derivatives will be calculated at all the grid points involved in one shot. You cannot do it separately for each point. So that is the way it works. Okay. So we just had a brief look at how things work in finite difference. If you look at the integral forms, then you will have to do similar things to get the corresponding expressions for finite volume. I am again not going to spend much time on this, but this is a matter of recapitulation. Just to remind you, we talked about explicit, implicit, accuracy, stability. There are so many things, right? How do they show up in somewhat simpler equations? Because Navier-Stokes is a complex system of equations. If we look at Navier-Stokes, sometimes we fail to understand how things are working. So you come to simpler equations which you may be aware of again from your OD, PD courses, and then you see you have Laplace equation here. Somewhere in your fluid dynamics course you were taught potential flow. Remember, potential flow past a cylinder. So we are discussing cylinders. So there comes your potential flow past a cylinder solved using Laplace equation. You remember, you put, what did you put? You put a doublet and then you put uniform flow and you had a streamliner on a cylinder, right? So how we solve it is actually by using Laplace equation. If you were to do a finite difference discretization, this is second order derivative involved in x and y direction. So you just learned how to do it along the x direction in the previous slide. You just plug the expression here. Again you get a similar expression for the y derivative. The only difference is, instead of the steps along x, you will get f double dash y f of y plus h minus 2fy or plus fy minus h, something like that. But the thing is that here the function is purely in x, but the Laplace case the function is both in x and y, remember. So you just can't use x or y, it will be x comma y plus h, x comma y, and then x comma y minus h. That is how it is going to come. Alright. So that is what you plug in, and then you might actually see the approximation of this equation coming like this algebraic equation. I was telling you that the partial differential equation will ultimately convert into an algebraic equation. So there it comes. Okay. So what is this k plus 1 and k? I mean, let us not go too much into it. Just imagine that all this has to be done through iterations. It will not come in one shot, and k may be the level of iteration. Alright. This is an explicit form because if you plug in all these values on the right hand side, you get this straight away at the grid point ij. What about another way of formulation? You have the functional values at a number of grid points which you want to solve, and the values are known on the right hand side, but number of unknowns are there on the left hand side, and therefore they have to be solved in a coupled manner by using a system of equations. That gives rise to what is called as an implicit formulation. Alright. Usually explicit formulations, when you need to use such formulations in terms of time stepping, there is an issue of stability, while implicit formulations do not have problems with stability. Okay, they are usually unconditionally stable. This equation helps us solve steady state diffusion. What if we were talking about a transient diffusion? Then we look at a different model equation altogether. This equation was an elliptic partial differential equation. This is a parabolic partial differential equation, and there is a very interesting fluid flow problem which can be solved with this. You have two parallel plates, and the lower plate remains fixed all the time, you have a Newtonian fluid in the gap, and you suddenly move the upper plate, and then it starts dragging the fluid with it. Initially there was no movement of the fluid, therefore the velocity profile would be like a straight line, and then it starts taking a turn because the upper plate is dragging the flow along with it, and then over a long time this will actually have a linear variation. Okay, that is the kind of effect that this equation models. And then all these equations need appropriate initial boundary conditions. For Laplace equation, it's purely boundary condition, but for the Stokes first problem, as we say, we need initial as well as boundary condition. Okay, the initial condition is this, that you start from a no movement, okay, and then over time as you march the solution, the velocity takes up this shape. All the while the upper plate is moving, the lower plate is fixed. So those are the boundary conditions. So when we talk about initial conditions, boundary conditions, we first try to understand them with simple model equations, then try to implement it in Navier-Stokes, not the other way around. All right, then we will be able to hopefully connect with the concepts and then implement them well on the actual equation of interest for us. That way you can even implement an explicit formulation for this equation which will look somewhat like this, an implicit formulation for this equation which will look more like this, and then you will see that in an explicit formulation you will get these values at each grid point separately by just plugging in the values on the right hand side, while these have to be solved as a system of equations. Again, we can show that this equation will have a stability limit. You cannot choose a time step larger than this stability limit that defines it. Okay, therefore if you take a time step beyond that limit, the solution will become unstable. Okay, what will happen? Gradually the solution will start generating very absurd numbers and then may crash with not a number kind of a situation in your computer code. Try writing a few lines of code for these simple models. That's how you start doing your CFD on your own. I am spending a little time on this just with the intention that many of you will venture out into this, and tomorrow you will write a Navier-Stokes code of your own. Alright, and then Professor Alam will be very happy. Well, we have a Navier-Stokes code coming from that GIAN course participant. We can plug it for our car study. Okay, so that will be a great thing to do, and that's when we hand over the charge to you and we move out of the scene. You can take it forward from there. So there's a little bit more. There's something called as a von Neumann stability analysis which we perform in order to get all these results. So explore if you don't know about it already. Similar things can be done with a wave equation, which is a hyperbolic PDE. Usually these kind of equations are encountered in compressible flows. So we were talking about solving Navier-Stokes in its compressible form. So when we do that, there are different kinds of wave features which show up in such flows, like strong compressive waves, expansion waves, shock waves and things like that. So they all exhibit wave-like behavior, and this is the simplest kind of equation that you can think of where you see a wave behavior being simulated, but that wave is a linear wave while a shock wave is a nonlinear wave. Okay, so there are differences. Again, same thing, explicit, implicit formulations. What is working in the background? Those Taylor series are working in the background. All right, and it depends on how you arrange them, how you apply them, that you end up getting explicit or implicit schemes. Notice that for an explicit scheme, again you have a stability criterion, and this is a very important number that you will come across in CFD, the CFL number, the Courant-Friedrichs-Levy number, as they say. While the implicit scheme doesn't have any stability limit. Crank-Nicholson is a very, very important scheme in even incompressible Navier-Stokes simulations. Okay, there are reasons behind it. I'll not go into the details now. So we'll just sum up with a few points regarding the accuracy of a numerical scheme. So higher order schemes usually need higher stencil sizes in general than lower accuracy schemes. Higher accuracy schemes can achieve reasonably satisfactory resolution of the solution features even with a moderately coarse grid. What that means is that even if you have a slightly coarse grid, the flow structures that you are trying to capture say the vortices and things like that, they can be still captured pretty well if you give a high resolution, a high accuracy scheme, a little bit of a coarse grid, because it manages to offset that coarse grid effect with its inherent accuracy. The same grid, when applied for a lower order scheme, will probably give you very inferior results. Alright, so that's the motivation behind using higher accuracy schemes, though implementing them in the Navier-Stokes codes is more involved. The truncation error, which you remember from the Taylor series expansion, the one that we dumped, that we forgot about altogether because we wanted to ignore it, just to make our life simple. So the truncation error reduces linearly on a first order accurate scheme. The first order accurate scheme was what we discussed here, where we just took 2 points and we tried to approximate the first order derivative by doing a one-sided difference. This gives you first order accuracy because the answer lies here in the truncation error. The first term has a h raised to the power of 1. That raised to the power of 1 gives you the first order accuracy. Okay. While in the second slide you will see that when you tried applying it to the second order derivative, you had a h square here. So that's second order accuracy. When this first order accuracy was done with a separate stencil, the symmetric one, it has a second order accuracy. So that's how the accuracy gets decided. Okay. This is what we call as formal order of accuracy. So with first order accurate schemes, what happens is the truncation error reduces linearly, and it reduces quadratically for the second order accurate schemes, cubically for a third order accurate scheme when you try to refine the grid. What does it mean? Suppose you have a two-dimensional space and you have deployed 40 points by 40 points along the x and y directions, okay, and you are trying to solve a flow problem, let's say flow on a flat plate. All right. So the truncation error that you are committing at this point with this grid, if you want to reduce it, let's say you make it 80 by 80, then what have you done? You have refined the grid by a factor of 2. The truncation error would reduce to half of what you were getting in the earlier case if it is a first order accurate scheme, to 1/4 if it is a second order accurate scheme, to 1/8 if it is a third order, and therefore you see the accuracy is increasing very rapidly. That means your errors are dropping quite rapidly if you increase the order of accuracy of the scheme. That's the primary motivation behind doing that. Okay. Let's move on. Another error I talked about was, and these are very important because when you apply these solvers and you are trying to solve those very complex features, you remember yesterday Professor Alam was showing us some kind of a conical vortex coming from a corner of the car, right, and it has very complex features. If you want to capture it properly, there are many things you have to do. One is you have to have a very nice mesh in that region. Second thing, you need to have a very high accuracy schemes which is solving the flow around that region, and that accuracy has two main aspects. That is what we are trying to represent here. That is the dissipative accuracy and the dispersive accuracy of the scheme. Here we talk about error because, you know, the more accurate it is, the less the error. That is the way it is. Okay. So let's say you are talking about some kind of a step function which is propagating in this direction, and you allow it some time to move in this direction. So if your numerical scheme is based on discretization of the first order wave, the linear advection equation, then what it will do is it will just translate this step function towards the right without distorting it. Neither will it amplify it nor will it dampen it, and also not create any kind of phase shift. Okay. Now numerical schemes inherently have error because we have that truncation error part which we are getting rid of. Naturally they will distort that step shape as it advects. After a while you may see that the corners have been chopped off, okay, and they have been rounded like this. This is what is called as the dissipative error. Okay, there is some kind of an artificial viscosity which is working, rounding off the sharp things. So there is no molecular viscosity which is playing role here. It is a numerical viscosity which is playing the role, and that gives you the dissipative effect. That means sharp things will be rounded off. So a sharp looking vortex structure will be kind of rounded up, okay, and then its edges will become blurred and things like that if the scheme that you are using to capture that has this problem in a dominant way. This is a different kind of a problem. This is called as dispersive error. What is that because of? It is because this depth that you have created over, if you were to do a kind of a Fourier decomposition of that, it would comprise of many components, right? You can actually superimpose a lot of, say, sine functions in order to get to this, okay, with varying amplitudes and frequencies, wavelengths. So if you were to decompose each component and then ask the numerical scheme to advect each one of the component, you will see that the numerical scheme shows up phase errors in propagating them. So it does not propagate necessarily with the theoretical speed of the wave. Okay, it either slows down or it speeds up. And then if you have a lot of those components whose errors are getting superimposed, then you have these structures. So you can actually start seeing those components, some of them slowing down, some of them speeding up and piling up in a very strange way to show wiggles around the corner. So this is what is called as dispersive error. Your scheme, your solver should not be suffering from these errors in a big way, because then when they are used to solve those complicated flow patterns, they will inherently corrupt the flow features. They will bring in all these things artificially, which you will think are physical features, but they are not. That is where we have to be very careful about. Usually the first order schemes, the lower order schemes, they suffer from this. Second order schemes suffer from this. Then comes the aspect that you have to impose appropriate boundary conditions, right? So going back to the Ahmed body, so if it is on the floor of the tunnel and it is a fixed floor, a fixed wall of the tunnel, then what do you impose over here when you are solving Navier-Stokes? You say that in a planar problem, the u component and the v component of velocity have to go to 0. That is the no slip condition. While if it is moving on the road and you are trying to simulate that, then you might like this road to be moving in this way if the car is moving this way, because that's the relative movement between the car and the road. Alright, therefore we make this as a moving wall in that case. How do we impose the condition? Which component of the velocity is going to be other than 0? It's only the u component, because that's along the x direction. The v will remain 0, but the u will be the same as the velocity of the car. Alright, so it's going to be imposed the other way around. And then you have to impose a velocity profile here. For very simple simulations, we try to provide a uniform flow here. That is the kind of idealization we make. As I said, we simplify things and we try to work them out, and then you try computing it. What has to be applied here or here? So this is going to act like an inflow, alright, which is allowing flow to come into the domain. So this is more like your computational domain. It may be usually much larger, but I am here reducing it, shrinking it to a region close to the interest, region of interest. Alright, so this is the inflow boundary. The flow comes in from here, the flow is expected to leave from here, so this is an outflow boundary, and this boundary is usually quite far from the body and the wall, and we usually see that the velocity gradients will become vanishingly small over there. So that's what basically leads to a zero shear boundary. I think Professor Shane was talking about zero traction kind of boundary conditions yesterday. So it correlates with that. Okay, so now on the body again, the flow cannot slip with respect to the body, right? The flow is moving at a huge speed around the body in general, but the layer which is next to the body cannot move. It is sticking to the wall, and therefore on the body you again have to impose the uv equal to 0 kind of situation. Now when it comes to the actual three-dimensional body of the car, then additionally the v component also has to be set to 0, both on the surface of the car as well as on the wall if it is a fixed wall, or if not, then only the u component will be equal to the velocity of the car, while the v and w components will be 0. So that's how we talk about boundary conditions here. Additionally, you see that the flow properties of the boundaries have to be appropriately defined, not that at each boundary we will be able to impose the exact values. Let's say the pressure and velocity, we may not be able to impose them exactly in terms of certain values at each boundary. We may actually have to do a mixing and matching. We may have Dirichlet conditions in some places, Neumann on the other, which means the actual values or the gradient is very small, equal to 0 kind of situation. Mix and match which make it consistent. So that is again another little bit of an area of complication, so we will not go much into it. Then we have to simulate the atmospheric conditions. Well, that is again remembering what Professor Alam mentioned, that if we impose a uniform velocity here, we may not be doing justice really. Okay, so the wind conditions etc. which may be existing, in that case we are overlooking it altogether. All right, so that is another. I mean, we have to rationally impose the boundary condition there, and then that's that. I mean, we have more or less discussed that. Now coming to analysis of results and validation, the post-processing step. So the intention of the post-processing step is to draw meaningful inferences from the large amount of numerical data that you have generated. As we said, that we may end up getting millions of values coming from those large number of grid points. So you have to draw meaningful inferences from all that you have generated. So what would you like to generate? Obviously for a vehicle you would definitely be interested in its drag and lift, and if there are side winds, then what kind of side forces are produced, or if there are any kind of toppling moments which are being produced and so on. That is definitely there, and the root of that prediction lies in predicting the pressure and the skin friction on the entire surface, because basically those forces and moments come out of an integration of the pressure and skin friction distribution. So by making appropriate plots, compare the CFD data with reliable experimental data to check whether the numerical model is working. So this is basically the validation step. You know, the first time you do a simulation, you try to make these validation checks and check how well your predictions have gone with respect to some kind of experimental data or earlier available numerical data. So that will prove whether your model equation choice has been consistent, the numerical approximation accuracy, its dissipation dispersion characteristics are good, whether we have taken care of the appropriate model, whether it should be 2D or 3D, and in the Reynolds number that we have operated, whether we should have done 3D and so on. Understanding of the flow physics to interpret the reliability. So all that is, you know, part of the validation basically. Once we are happy with whatever checks we want to do over here, then we look at numerical flow visualization. We would like to plot velocity vectors around the car body, contour plots of pressure, Reynolds stresses, etc. And remember that your probing can go very deep into the flow because you have a large number of points in and around, around the body surface as well as in the neighborhood in the flow. Alright, so wherever you want to probe, whichever region you want to probe, you have to define it appropriately through your post-processor software. That I want to see this plane, I want to see along that line. Whichever region you pinpoint to, that particular software should be able to give you the details along that line or in that plane, etc. So obviously you have to learn to use the post processor, that goes without saying, and I guess I forgot to mention earlier that there are a lot of softwares available to do all these steps, starting from the pre-processing to the solver to the post-processing. There are different kinds of softwares available, right? So in the pre-processor, for example, I mean, you have commercial softwares, you have open sources, like say you have ISM CFD on one hand, you have PointOIs on another. When it comes to solver, you could be having your in-house solver, you could be having let's say commercial solver like say Fluent, you could have open source solver like OpenFOAM. In post-processing also you would similarly have post processors available, right? One of the very good open source post processors which I think you all should be exploring is ParaView, for example. Okay, it's a very strong post processor and it's absolutely free to use, no licensing issues, nothing, while you may face licensing issues with TechPlot, for example, right? And these are also important bits of information, because when it comes to practicing CFD, you have to check availability of such resources. If they are not available, whether if you are using any licensed software, then whether you can purchase it through your institute or department, whether you have the money for doing that. If not, the good thing is, if not, there are abundant open source resources. Nobody charges anything for that. Only thing is, learning may be a little more difficult because there is lack of documentation, but however, there are very large user forums, so if you spend a little more time following all that, you should be able to learn it, and from tomorrow you become completely independent, okay, with a very strong resource, very strong software, but no money to be charged for that, right? So that's great. Okay, so next point is to show the variation between a dependent and independent variable. You may like to use XY plots. We have been doing it for so long, is it not? For example, CP variation as a function of theta on the surface of a cylinder. Professor Shen was showing us a lot of that yesterday regarding his research. He was looking at how things were varying along the surface of a cylinder. He was also looking at what was happening in the wake. So if you look along the cylinder, then it could be something like, you may like to go along the theta direction, so you show theta as the independent variable, and along theta you may like to show the CP, which becomes the dependent variable, and there is your XY plot. So you would have a nice CP distribution on the cylinder, right? Similarly, if you want to look what's going on in the wake, for example, you show it as x by d or something like that, if d is your diameter or some characteristic length scale, and then on the y-axis you show the the dependent variable. All right. So it may be what? It may be Cp, it may be a velocity component, it may be kinetic energy, it may be some Reynolds stress. So there could be n number of things. All right. So these plots are also extremely important. It's not that we are always going to forget things just by looking at the contours, the nice colors which are deployed there. A lot of us like to call CFD as colorful fluid dynamics, right? So colors are nice, colors makes you happy, and at the end of a long struggle, if you see those colors, you will be absolutely ecstatic about it. I understand, but then don't forget these plots, okay, because the plots go a long way for quantitative comparison. You remember what Professor Shen was showing? Most often he was showing plots, he was not showing colorful fluid dynamics, because the plots gave us a much better feel as to how things were comparing, either with experiments or with other numerical data and so on. Okay, so now we come to interpret the flow physics. Very, very important. Choice of an appropriate flow visualization tool is important to understand the underlying flow physics. So flow physics in the sense that what are you trying to study here? Okay, are you just happy with lift and drag? Are you just happy with pressure and skin friction distribution? Are you just happy with just seeing what's happening to your velocity vectors just around the body, or you need more? That needing more has to come from an understanding. Okay, for that you have to of course explore it more, you have to read up more, you have to look at existing results, look at big books which report about all this, very interesting journal papers which are coming all the time. That means there starts your effort to understand the flow, to understand the physics, interpret the physics, okay? And the better you can interpret it, the better you can study it, the better you can implement it in whatever numerical investigation you do. So tomorrow when you do an investigation on the car body, your investigation will have a different depth, a different level of investigation, okay, which goes much beyond what has been done traditionally. Then people will just rise up from their chairs and say, this fellow belongs to the new regime. It is not that old regime which just keeps talking about the same old stuff. They are getting the actual things which makes a difference, alright. So that step jump has to now happen and you have to lead that, alright. So interpreting the flow physics, never undermine it, because I think the new regime has to increasingly look at this. There's not much more that we need to do, I think, on the flow solver side or even the pre-processor side. Today we have to increasingly concentrate on understanding the physics to a better level, a deeper level. Only then that can make more changes. Because the other day, you remember Professor Alam said that, we have already covered almost 90-95%. How about the remaining 5-10%? That journey is very difficult. Until unless you go to the core of the issues, you will not be able to do that incremental change. That needs physics interpretation, definitely, okay. So for example, you may not be just happy plotting vorticity contour, okay. You may like to look at a more contemporary tool, of course, which has been around for quite some time already. They say that all these vortices which are floating around, they belong to a category we often like to say as coherent structures, okay. And identifying structures with certain criteria, like Q criteria. Okay, I leave it to you to explore what that is all about. I'm not getting into it right now, but it seems, because this tool has been used on different kinds of problems, that it's a very effective tool to look at certain vortex dominated flows. Okay, it can really go deep into the flow structures and show them with clarity to you, which is often missed out if you are just looking at vorticity contours or streamlines or even Reynolds stress plots and things like that. So it makes a difference, and there's a physics behind it, why it works so well. So you have to understand that physics. Sometimes overlapping of multiple features on the same plot helps in a better correlation. That we have learned through our own experience. That plot pressure contours, plot streamlines on that, and then you have two features talking to you simultaneously and probably pointing more things to you than just one of those features could have. Even if you make two separate plots and put them beside each other, you may not always find the connection. So overlapping both in one plot could actually do magic. But till you strike the balance that which two are talking to each other best, that is what we call as the correlation. That these are strongly correlated, or that is weakly correlated. You remember about correlations? We often do all this in turbulence. So that is happening with different attributes. Which attributes are talking to each other strongly? That means they are well connected. And if you superpose them, then you have a better way of interpreting things. So this again can do magic for you. We have seen that happening through our own research, for example. So pressure with streamlines, vorticity contours with streamlines, many other things clubbed with each other. You have to do a lot of experimentation. Once you have those numbers, it's all up to you to explore. You know, it can do magic for you. It's up to you to do all these hit and trials and then get a feel that which combinations work best. Okay, solver selection. Okay, now what we are trying to talk about over here is that finally we are trying to sum up the things again. So let's say we are doing all of this for trying to compute flow past this mammoth body. We are just trying to sum up again from the beginning quickly. So solver selection and setting up the simulations. A suitable numerical solver needs to be used. It could be in-house, open source, commercial, like what we have mentioned here. Choosing the fluid flow equations for this kind of problem, there's no uncertainty here. That's a good thing. Straight away incompressible Navier-Stokes. But if you are doing CFD on other problems, you are the best judge which equations have to be picked and solved, right? And you of course choose and define a computational domain. This is a truncated form of that. This actually could have been much larger. We have zoomed into this region just to show the details. The solver discretizes Navier-Stokes equation using a suitable technique, that is your choice again, and solves them usually in an iterative manner to predict the flow behavior. And then there is a question, when do I stop the simulations? If it starts, it has to stop at finite time, right? So simulation parameters such as time step, convergence criteria, these need to be kind of defined. Other solver steppings have to be appropriately chosen, which includes the accuracy of discretization schemes. So like you have chosen time step size, you also set a criteria that, well, if the solution converges to a certain level, I would like to stop there. So there needs to be a criterion defined by you that, well, I'll stop after either solar or I'll stop if the solution has converged. What does it mean if I say converged? It means that at each and every grid point that you are solving, you are time stepping the solution, right? Things are changing incrementally as it moves from one time step to the other. You keep monitoring the changes over two successive time steps, that what change occurred in velocity, in pressure at a grid point, and for all such grid points. Okay, so you may actually have a RMS measure, for example, to include the effect of changes all over in the domain, and set a criteria that if the RMS change over two successive time steps reduces below this, then you have reached convergence and you can terminate the solution. And the solver could be told a priori. You don't need to sit in front of the screen for hours just to figure out whether that has happened or not, because you may like to go for lunch and come back. Okay, so you just tell the solver in advance that watch out, if the convergence goes below this, you stop immediately. And then once you are back from lunch, you will see that it has terminated. Your numbers are now available for all the post-processing to be done. Okay, post-processing and analysis of numerical data. So when the CFD simulation is executed, the solver computes the different flow field variables, velocity, pressure, turbulence, etc. Post-processing tools are used to visualize. We have already discussed it just now. All this is kind of done. Now comes a very important point here: design, iteration and optimization of the car geometry. Okay, so let's say you have done the first simulation with the geometry that you were given and you are happy. Okay, I got all the results consistently. So what have I proved? I have proved that I have chosen the correct solver, I have done all the settings correctly, I have chosen a good grid, I have chosen an appropriate time step, grid spacing, everything is done fairly well. That's why I have got a good result with one particular geometry. Now tomorrow the car designers come back and tell you, oh no, that geometry has changed, and for a while you are perplexed. That means I have to do it all over again. Yeah, it has to be done again. So who's going to give you that new geometry? Well, they would probably provide you the CAD model of the same, right? Their CFD team will provide you the CAD model, and then with the same solver settings, etc., most probably you don't have to touch those things. Hopefully you again run it, and hopefully you'll again get nice results, but the results will change somewhat. So you go back to them and tell them after your analysis that, see, the drag has come down from 0.3 to 0.28 or from 0.26 to 0.25, and they may be happy. They may be worried if it has gone up from 0.24 to 0.26. Okay, then something is going wrong somewhere. So a sequence of CFD simulations are performed to allow for design changes and optimization, a very, very important step. All right. By modifying the vehicle's geometry or adding aerodynamic devices, engineers can access the impact on performance metrics like drag, lift, stability under side vanes, etc. There could be so much more. Professor Alam is the best person to tell you more which other performance metrics are important. Alright. This iterative process helps in improving the vehicle's aerodynamic efficiency as well as performance under different operating conditions. So they will also tell you that these are the operating conditions under which you have to run the simulations and show it to us. We are not happy if you just show it at 80 kilometers per hour. We need it up to 150 at least. And then they say that at 120 if it is running and there is a side wind, we want to see what's going on with the new model. You have to do that too. Like Professor Alam turns his turntable in the test section and aligns the car at a different yaw angle, you as the CFD engineer have to now figure out how you are going to allow that skewed flow into the flow domain. Will your earlier inlet boundary do that job? Most probably not. Now you have to understand this, that let's say you go back, okay. In this planar problem, can you simulate the effect of side wind? That's the first question to answer. It's going to be a little difficult. Preferably, you extrude the grid and put in a 3D model inside, and then you try to realign the flow in a yaw direction which matches with their requirement. Now the problem with that is this boundary will no longer act as the inflow. One of the lateral boundaries will also participate as one of the inflow boundaries along with this inflow boundary. Alright, what does that mean? Well, can I have a box like thing? Okay, this does the job. So what I am trying to say is, this is your Ahmed body, let's say. Okay, I'll turn it the other way around. It looks more like Ahmed body now, right? Okay, and we are trying to say that, well, instead of the wind coming head on, it's turning. So now I can turn the model or I can turn the angle, right? So if you want to keep the meshing and all that intact, then you turn the flow, because that's the better choice for you as computational aerodynamicist. Now if it comes in here, earlier your inflow was just this boundary because it was coming head on. There was no mass influx from here, from the lateral boundaries. Now if you come from here, this lateral boundary will allow mass. So will this earlier inlet. That means the boundary conditions change. Okay. So the boundary conditions have to be redefined now, and you have to redefine the way the different boundaries are functioning, and then you will find that only this being the outflow plane will break down, because this and the other lateral boundary will allow mass outflux. Do you see that? Everybody gets that point? So this is how we do a yawing effect if you are looking at a problem like this. Okay, so things have to be reworked. That is the main message. We'll go back again. Sorry, we were here, I think. Yes. So the operating conditions, that's where we were at. Okay, so if they tell you that these are the operating conditions, their requirement has to be translated into your CFD setup. That translation is a very critical and a very vital exercise. A lot of understanding is needed there also. Like I said, that you need to understand the physics better to do the post processing. Similarly, you have to understand the physics very well even to start your simulations under different challenging operating conditions. So you have to take care how you do it. All right. Excuse me. Now we'll start summing up somewhat. So the CFD modeling provides vital insights into the flow behavior around the vehicle. It helps the concerned engineers to optimize the design to reduce aerodynamic drag, improve fuel efficiency, enhance stability, minimize aerodynamic noise, evaluate impact of design changes. Evaluating the impact of design changes can be done without need for physical prototypes. Aerodynamic drag becomes vital at velocities above 80 kilometers per hour, and therefore CFD simulation must be done in parallel with wind tunnel experiments to optimize and finalize the aerodynamic shape of a vehicle. So those are broad points. I'll also discuss about a few things which I very roughly took note of yesterday, day 4 lecture, when Professor Arnab was giving us a very interesting talk on flow visualizations and wind tunnel measurements and things like that. I saw a clear connection with the CFD over there. So remember, you were hearing from him about power spectral density plots, right? He was showing you, the wide range of frequencies which are seen and so on when they do the measurements with microphones and so on, or unsteady pressure sensors. And it seems from the PSD peaks, they can figure out whether it's a boundary layer separation or a reattachment unsteadiness fluctuation, or it's related to vortex shedding or breakdown. Like he was talking about a spiral vortex. So you know that spiral vortices in aerospace, they also occur for delta wings. And when the delta wings pitch up substantially, the spiral vortex starts breaking down. Okay, so it breaks down under a certain axial pressure gradient. Okay, and if the breakdown goes and enters the wing surface, then the wing will stall. Okay, so there could be catastrophic effects of that. So similar breakdowns could be taking place here as well. There may not be catastrophic consequences, I am not very sure about that, but there could be. So all kinds of footprints are coming from such physical effects into the PSD. There is also the broadband character coming from turbulence, right? So how do you capture all this in the CFD? As I said, you have to have a wonderful mesh so that you don't miss out the finest of scales. But most importantly, the flow solver has to be chosen with care. It has to be inherently a high accuracy flow solver with low dissipation and dispersion error. Until unless you do that, everything will go wrong fundamentally, and then you cannot recover. And these are required for capturing the different intricate flow phenomena observed on a modern car body. And there is the connection between modern day high accuracy CFD and reliable simulations done to compare well with experimental data. Okay, probably we have to bridge that gap further. I mean, we have to check whether we have sufficiently high fidelity methods being used in order to capture such finer details. We may be doing okay with less accurate flow solvers as far as the gross flow features are concerned, but as it goes into the finer details, you will start missing out if you don't have a high accuracy solver. So there are a wide range of eddy length and time scales which are involved in such flows, and these unsteady flow fields cannot be effectively captured with Reynolds average Navier-Stokes equations, which are basically time averaged. Okay, so you run a kind of a road roller saying that okay, I'll time average everything and I'll look at the turbulence, I'll not look at unsteady effects and so on. Then what you get is the Reynolds average Navier-Stokes equations. They are wonderful industrial tools, but have to be used with care, especially in flows which have a lot of flow separation, for example. So until and unless you get a good model from the runs end, probably you will not get so reliable results. And as far as unsteady features prediction is concerned, you will probably not be able to do any justice with that. That's where you have to look for better ways of tackling it. One way could be large eddy simulation, but if the aerodynamicist who is doing that tells you no, that's too expensive, he may tell you that okay, we have a reduced order form of that, and that's detached eddy simulation. Okay, so that's somewhat like a hybrid of runs and LES, and then it tries to kind of leverage that advantage and make it a little less costly than large eddy simulation, and therefore industry accepts it in a much better way than accepting LES as an industrial prediction tool. So maybe detached eddy simulation, which can still give you a good idea about the unsteady effects and the turbulence which is operating in the mid scales. Okay, so Direct numerical simulation may be too expensive, because this is the tool we use where we want to capture all of it without modeling, and that's extremely expensive. You may have heard about Kolmogorov length scales in turbulence, right? So your grid sizes have to go down to that order. Even if you are not exactly there, it may be few tens of Kolmogorov lengths, not larger. Otherwise you may not be able to claim it as a DNS. And therefore these kind of things have to be done in order to get reliable spectra finally. The spectra is a good reflection of what you have ended up capturing, right from the large scale ADs to the small scale ADs, all the way through. The spectra, if it shows you the larger scales, then you can say that, well, it has probably filtered out the small scales and hasn't captured it at all. If it has captured the large scales and also a good part of the intermediate scales, and the smallest scales have been kind of filtered off, then you are somewhat better. And if you have captured all of it, then you are best. And going in that sequence, it would be runs, alias and DNS respectively. Okay. So why does it matter? It matters in the sense that you have reliable predictions of all this. You are also ensuring that you have captured all the dynamically relevant modes which should have existed in the flow. That means all the energy which should have been there in and around the body has been captured well, which ultimately means the physics has been captured reliably. And now if you know how to predict the physics well through your own knowledge and training, you can do wonderful things and probably give enormous inputs to the designers, saying that probably a 1 or 2 degree angle change here to the curvature or something like that may do wonders to your sound pressure level, to the flow separation reduction, etc., etc. Again, we heard that hydrodynamic noise and acoustic noise may have to be captured together, and there is a huge gap between the two, right? So low accuracy schemes will probably do a good job doing this, but they will not capture this at all. That's the problem. And then if it is important for the car company to find out the sound pressure level, the noise, aerodynamic noise, then it goes missing altogether. And the difficulty is that you are talking about capturing very strong signals and very weak signals simultaneously, where the weak signals should still be retained without being overwhelmed by the presence of the strong signals. That's always a challenging situation. High accuracy schemes can also do that. Okay. We say usually that when we try to check accuracy of a scheme, one way is doing it the formal order of accuracy, that is the truncation error, the Taylor series way. The other way, which is a little more advanced but more contemporary, is what is called as the modified wave number approach. In that we get to see that at the higher wave numbers, which are usually associated with the smaller scales, how good is the numerical discretization scheme doing in capturing those features. If you can stretch up to a good extent of the entire range of high wave, modified wave number, then your scheme can do wonders as far as all this is concerned. That's a more relevant check to do. Of course, high quality mesh is a definite requirement, and that can capture you all these detailed features like A-pillar vortex, which Professor Arnab talked about, the aerodynamic noise, which is basically coming out of pressure fluctuations, the sound pressure level, etc. All that can be predicted well. Then comes the this issue that if you are also interested to find out how far the noise might propagate to far off distances, then there are ways of doing that CFD too. So what you do is, near the body you have a very refined mesh, you have a very high accuracy solver working, and you capture all the turbulent eddies which are basically going to create that sound with a highly locally defined mesh and a LES DES solution, whichever is permitted. And then once you have captured the sound source accurately, now you are interested in trying to look at its propagation in the far field, right? Let's say 10 meters away, 15 meters away, if there is a person next to the highway, how noisy is it to that person? Then you have to complement it with a sound radiation model for far field propagation of sound, maybe on a coarser mesh. Okay, so there are models which can do this. That is part of computational aeroacoustics that we do, right? So these are things which the new generation will definitely look at, all right, and they need to look at, all right. So I think I just added this slide at the last hour because I recalled some of the points Professor Firoz told yesterday, and it sounded very interesting to me, very relevant to me. Okay, so I think with that I will come to the end of the first portion of my presentation, and we mostly discussed about the broad framework of CFD, what we do in CFD, how it fits into our vehicle aerodynamics and industrial aerodynamics. You know, without going too much into the nitty-gritties, it's more like a bird's eye view. And as the future generation, what are the directions you should be looking at? What are the directions you should be concentrating on? Okay, what are the skill sets you need to pick up? All right, these were the things which we mainly focused on, and we tried to generically look at the different steps of say the performing a CFD study on a, say, a generic car model or something like that. What are the issues, boundary conditions, and so on. Okay, so with that we'll have a short break now. We'll have tea, refreshments, and then we'll come back in a while, and then we'll look at a few test cases or case studies, whatever you call them. I just put them together in a kind of random manner, but I thought it may be relevant. Okay, so with that, thank you very much for your kind attention, for bearing with me so long, and then we'll meet soon.
সুন্দরভাবে বলেছেন, ওয়েল
কখন স্টার্ট করব আপনারা আমাকে একটু ইন্ডিকেট করে দিয়ে উনি ইন্ডিকেট করবেন হ্যাঁ Okay, welcome back after the break. So I hope you are not sleepy. You had some tea, refreshments. So we are now getting into the last session of today. And as I have mentioned in the previous slide, that we are going to look at a few case studies, not all of which will look bluff, right? So I mean, being from aerospace engineering, we all have a passion towards these airfoils, right? So never our story would end before we have done a little discussion about airfoils. And the other day, Professor Alam also very nicely explained to us that yes, we started from that airfoil and we somehow modified it because the requirements of a ground-based vehicle, it's different. You know, it's clean. It cannot be as clean as an airfoil because probably that would affect its mission objectives and so on. So we have to play with these shapes and get them to a different form in order to make sure that it's fulfilling its desired objectives. But nevertheless, there are lessons, important lessons to be learned from here, and that's why a little bit of a small case study which involves the computations of airfoils at different angles of attack. And I have picked up an airfoil which has been studied more recently. I mean, these are some of those airfoils which are called as the low Reynolds number airfoils. Okay, so with the advent of micro air vehicles and things like that, UAVs, MAVs, and so on, which I think is also part of our vehicle regime, air vehicle regime in the smaller scales these days. These airfoils have become more popular. So I have taken up an airfoil from the Epler series. So at the bottom you will see E61, that is basically Epler 61, and many of these airfoil geometry details are very nicely provided in the UIUC database, airfoil database. Okay, a university in the US has nicely documented this. So you can also review that for your further study. So several years back we were doing a project for some agency, and we were studying some of these airfoils, and we did some small experiments with wind tunnel models, made some pressure measurements and all that. We also did some computations, and I picked up some of those old results, and suddenly after having looked at a lot of these wake flows behind bluff bodies and things like that, it struck me that well, if I pitch up an airfoil to a significant angle of attack, even that starts showing significant flow separation, right? So apparently streamlined body can also act like a bluff body. The other day Professor Alam showed us that you have a very slender flat plate. If you oriented it 90 degrees with respect to the incoming flow, it starts looking very bluff. The CD goes way up to 1.2 or something like that. But if you align it with the flow, it becomes nice, streamlined, and then it has a very aerodynamically efficient orientation. CD is small, L is large, and so on. That means the L by D ratio would be very high. So those are the things which matter in terms of aerodynamic efficiency. So this first case study looks at different orientations of airfoils and what that might do to the flow patterns around the airfoil. What have we solved over here? We have solved incompressible Navier-Stokes equations, because we are talking about small speeds, in terms of few meters per second, right? And then you are just pitching up the airfoil to some angle of attack. That means the air stream as such is moving perfectly horizontally from left to right. It's the airfoil which is pitching up to a different angle of attack with respect to that airfoil. Okay, so the angle that there is an imaginary line connecting the tip of this, which we call as the leading edge, and the trailing tip, which we call as the trailing edge. So if you imagine there is a straight line connecting the two, then there is a certain angle that straight line makes with the incoming flow, right? So that straight line and the inclined chord line, that included angle is your angle of attack basically, right. So in the first picture you have a certain angle that's 12 degrees, in the second it has increased to 15, third it has become 25 and so on. Usually when you would deploy such a section on a flying vehicle, you would deploy it at low angles so that it can generate a good amount of lift but doesn't produce a lot of drag, which can happen if your flow is nice and smooth on the airfoil surface with virtually no separation. But incidentally at 12 degrees it's already showing a little bit of a separation pocket, right, and as you pitch it up further the separation pocket increases, and further there is a large scale separation here. So imagine if I am talking about a curved surface on a vehicle, then this also indicates that if the curvature is such that it is mildly tilted back, then probably the flow will remain attached. If you very dramatically tilt it back, there will be quite a bit of flow separation. So that's a clear-cut understanding that we can derive from this, though the actual body of that vehicle may not be visible here. We are just like looking at only one part of it in an isolated manner. Again, if you were to find the pressure distribution on the surface as it changes with the angle of attack, the pressure distributions may look quite different. And the most important thing is that if you make a plot like this where you have the x by c, the c is the chord length as we say. In the case of a cylinder it's the diameter. So these are important characteristic length scales depending on the kind of problem that you are looking at. Then the dependent variable that we are plotting here is the pressure coefficient. It's the non-dimensional pressure that we talk about, right. So interestingly you will see that the different plots that we have with the different legends indicated, you will find that all of them seem to reach a value of 1 somewhere close to this x by c equal to 0. That is basically happening here. This is called as the leading or leading, say, a stagnation point. Okay, so there is one particular streamline which is coming and reaching this body and just halts at the body surface. So that's a stagnation streamline. Okay, and the point at which it halts is what is called as the stagnation point. The other streamlines make their way above or below the airfoil, okay, and then try to follow the profile and so on. Okay, and this stagnation point location changes a bit as you pitch it up more and more. You notice that the stagnation point is going further downstream. Okay, if it is perfectly aligned with the flow, then stagnation point will be closer, to the leading edge itself, and exactly the leading edge if the geometry of the body was more symmetric. Here the geometry is slightly asymmetric about the chord line. There are other kinds of airfoils where if you imagine that this chord line is a straight line and there is a equal distribution of thickness about the chord line, then you would have had a symmetric section. So that is called as a symmetric airfoil. This is called as a cambered airfoil. Okay, camber is often very important for generating lift, by the way. Okay, so we understood this pressure, and then there are regions of negative pressure coefficients, which basically means the pressure is going well below the free stream static pressure. Okay, so there are such regions, and then they seem to level out as they move towards the trailing edge. And you notice that once the large scale flow separation starts, the area that is enclosed between the upper and lower curves, which are kind of acting like an envelope, that is basically indicating the pressure difference between the upper and lower surface, that keeps growing less and less. That means it's generating less and less lift if those curves are getting closer. So it will act as an effective lifting surface if it is well spread out. It's going to, if it comes closer, then it's not acting effectively as a lifting surface. So these are the basic inferences one can draw from such things. Okay. Now what's going on as far as the fluid mechanics is concerned? Okay, for a while we seem to be far away from CFD, mathematics and those equations and all. This looks closer to the physical feel of the flow. So when it is a low angle of attack case, most of the flow is attached, Okay, the streamlines are nicely following that contour and so on, and then you will find you will have a very narrow wake here. Because you are talking about Navier-Stokes solutions, okay, there would nevertheless be a little bit of a wake. Okay, why? Because there is some momentum loss which happens in the boundary layer. Okay, no matter how hard you try, you cannot avoid that, and consequently there will be a momentum loss in this small stream which is going downstream. Okay, in other regions of the flow, the momentum will be more or less conserved, and the drag acting on the body has a connection with that momentum loss. Okay, that's one of the methods by which we try to estimate drag on a lifting surface. One way is to directly do it with balances, load cells. The other way is to estimate from the velocity profile here in the wake. Now what happens as you increase the angle of attack? We find that yes, it starts behaving like this, that the boundary layer on the upper surface, you know, starts separating beyond a certain point. It does not happen, by the way, on the lower surface. We can show, we'll actually try to show it through some plots in the next slide, that the lower surface is never challenged in terms of the pressure gradient that it faces. So it's a so-called favorable pressure gradient. You might have learned all this in your fluid mechanics course already, and that's why even though it has pitched up quite a bit, there's no sign of any trouble on the lower side. It's nicely following the surface, but there seems to be a problem here. Okay, so this will increase further and further, and this separation point will keep moving further upstream towards the leading edge as you keep pitching the airfoil section up and up and up to larger angles. What's happening to the boundary layer? If you look at a point like this, the boundary layer still looks quite fine. It's attached on the surface, and there's no sign of any difficulty here, in the sense that you don't see any odd profiles. It's the kind of boundary layer they draw for flow over a flat plate. Okay, you remember some of you may have learned the Prandtl's boundary layer theory, a little bit of Blasius solution and all that, right? So there they talk about such a boundary layer, though the surface is actually curved, because this is what it is. But as you move down, let's say a point like this, there the velocity profile looks more like this. This is indication of trouble. You have a very small velocity or virtually no velocity at this point near to the wall, and if you move a little further, the velocity would actually turn the other way around, and that's the signal of flow separation. How do you understand that that's the point of separation? If you plot the skin friction coefficient along the surface, you will find a point where from the skin friction being positive, it will go exactly to 0, and then beyond that it will go to a negative value. That's the indication of flow separation. The most reliable way to find out where the flow is separating. Instead of just looking at streamlines and velocity contours, this is the most reliable way. Always remember. Okay. There is a so-called inflection point in this velocity profile that I leave it to you to explore further on this. Now, then what we are talking about basically is that if we were to look at what's going on to the flow, if I have a small domain around the airfoil, more like that computational domain we were talking about in CFD, this is more like a black box. Okay, we just see that the flow comes in horizontally and it takes a turning after it goes out. So that black box somehow turns the flow. Okay, and as a reaction we find some force acting on this body. Okay, purely from momentum conservation you can argue like this, that if you are doing this, then the force is a direct outcome, because you have made the velocity vector to turn through an angle. There will be definitely a force associated with that turning, and if that turning has happened, there is bound to be a lift acting on that body. Okay, try to argue from a momentum conservation point of view. Alright, and then if you do it for a range of angles and then try to find out how your lift coefficient has varied, then you will see a nice plot going up in a linear manner like this as a function of alpha. And at lower values of alpha, though this is not all that clear, the streamlines are nicely hugging past the body. At higher angles this is what happens, and it dips down. Okay, your Navier-Stokes predicts this dipping down because it can capture flow separation, it can capture the effect of flow separation on the body. If you were to do an Euler solution for the same problem, then this would never dip down because it's modeling inviscid flow. It will not be able to capture separation on its own. So this is how it works. And if you were to go back to the velocity profiles and how the pressure makes a difference, etc., this is your flat plate. Okay, in a fully developed flow, the velocity profiles virtually remain invariant as you move down the plate, and you find that the static pressure doesn't seem to have any variation as you move down. Okay, the moment you change the shape to something like this, then the whole thing changes. Okay, so tilted surfaces do a lot to how the flow will behave, right? The flat surfaces don't do much. So the tilting, again, the direction of the tilt is very important. If you look at the lower surface, it's something like this. Okay, nice robust boundary layer. That's just because the pressure, the static pressure keeps reducing as you move along that lower surface. If you were to plot it that way, it will be a nice looking reduction, which we call as the favorable pressure gradient. That assists the boundary layer to remain stable, steady, robust. Okay. If you look at the other side, on the contrary, the static pressure incidentally keeps rising, and that is something which is pulling you back. You are trying to move ahead, trying to stick to the surface, but it's, you know, holding you back towards the rear direction. Already the viscous stresses are there which are pulling you back. Additionally, pressure joins them. Now you have virtually no chance of winning over them, and that's the consequence what is produced. You try to find a path to run away and not face this terribly increasing opposition. All right, so you can't rise uphill along this pressure, and therefore you find an alternative. That's nature's solution, of course. Our Navier-Stokes solution doesn't decide the physics. Navier-Stokes at best tries to model it, but the physics inherently, which comes from Mother Nature, decides that the flow would take that path. It will not try to go, you know, into a battle with the increasing pressure, but rather find a easier way out and take a different course altogether away from the surface. And as an aerodynamicist, you have to appreciate this, because this has a lot to do with how the body will aerodynamically behave. Your lift, your drag, everything depends on this. So what happens to the velocity profile? It was looking nice, but then it was decelerating, losing momentum. Here comes a point where tau becomes 0, that means your skin friction is 0. Here it has become negative. The flow has turned the other way around. Okay, so this is typically the velocity distribution near a separation pocket. And when you do bluff body aerodynamics, you need to have a fairly good understanding of all this. Okay, this is where your boundary layer solution will break down also. So all that is there, and we have just tried to sum up some of the points related to the physics. Okay, so having a curved airfoil section or inclining it at an angle to the flow does not guarantee sufficient lift generation. No way. Okay, that will be guaranteed only up to a certain angle. There is no free lunch. The flow needs to remain attached to the airfoil surface to turn effectively and generate lift, but that Mother Nature decides up to what angle. Adverse pressure gradient on upper surface of airfoil, which is also called as leeward surface, increases as the angle of attack increases. That is the trouble. Adverse pressure gradient causes flow separation. The other thing is the state of the boundary layer. A laminar boundary layer is more prone to separation than a turbulent boundary layer. So if you had some way to turn this flow turbulent, turn the boundary layer to a turbulent boundary layer, probably it would have managed to stay on in an attached manner to a little greater extent. But if it is laminar, there are lesser chances. Ineffective flow turning due to flow separation occurs beyond stall angle. So you remember that CL curve dipped down. So this is what we call as stall. Okay. This also works in your turbomachinery blades. You remember? There is blade stall. There could be rotating stall. So all kinds of things can happen there too. Okay, drag increases dramatically after stall, so you have loss of lift, you have increase of drag. So what will happen to your aerodynamic efficiency? The lift to drag ratio, as we say, that will suffer very badly. That means it's not going to be an effective aerodynamic surface anymore. The L by D ratio indicates aerodynamic efficiency. It dramatically drops after stall, and you cannot say that it's going to act as a good lifting surface. But as a car aerodynamicist, you may not care much, because you may say there's no way I can prevent this somewhere or the other on the car body. Let me accept that. And as Professor Alam said, that in order to prevent this problem, if I make the car trailing part so shallow, then it will become a long boat tail and nobody would buy your car. Neither would you find it easy to maneuver through the roads of Allahabad or some of the busiest cities of India, because it will be a long car. Okay, how can you take your turns at the roads or through narrow lanes and so on? So there are maneuverability issues. You are not flying in the air after all. So there are practical constraints. So therefore you have to probably go for this here and there. The other thing is, there is something called as 3D relieving effect. Okay, so the way the flow separates here on a 2D surface is not identical to how this would have separated if it was a 3D surface, because there is a third direction, and along that third direction there are other things which will happen to compensate, and there could also be flow kind of rolling up from the finite edges of that surface. But if you curve it around into a closed surface, then the flow may not behave like that at all. So car aerodynamics may not be so simple to analyze purely based on airfoil aerodynamics. Be careful about that. Now a little recap of what's going on the surface of the airfoil. If we were to imagine that there is also a span-wise direction, though strictly speaking in a planar sense we don't see that dimension, then you take a small strip of an area which moves all along the span and has a small extent here. So there is a small elemental area you have created, and there is pressure acting normally on it and shear stress acting tangential towards the rear part. Basically you have to integrate the effect of pressure and shear stress on the body surface all around and create the resultant force which arises out of it and the moment that arises out of it. Okay, so when you compute moments, you have to have a reference point. You could compute moments by taking the leading edge as the reference point, or quarter chord point, or mid chord. In aerospace engineering we have that quarter chord as a very interesting point for low speed aerodynamics. But in car aerodynamics you have to similarly define that how have you defined your pitching moment, rolling moment, yawing moment. Probably yawing will be very relevant for you if you have a side wind and so on. So there also you have to define a point about which you are computing the moments. And why are the moments arising? Because about that point the forces, the elemental forces, find a moment arm to act. So there is some kind of a torque effect. So a force acting at a distance from a point means there is going to be a moment, right? So that's how the moments sum up. So here it sums up on this body. On a car it sums up in a more complicated manner in a three-dimensional sense. And then effectively what is going on is a resultant force and a moment which acts. And left on its own, this body would probably keep pitching like this because there is a moment acting on it. Would you like to have that? Because it will finally topple. So you have to compensate for that by creating some other compensating moment, and therefore in aircrafts you may like to use some other surfaces to compensate for that moment and stabilize the body. Okay, so this is called as a pitching moment. So probably you will generate just an opposite pitching moment using some other control surface. Try to find out about that. If you look at the resultant force, it works in certain direction, and then you can have it resolved along some important directions of interest. If you resolve the components along the flow direction and normal to it, then what you end up getting is drag and lift. Okay, if you try to do that force resolution normal to the chord and parallel to the chord, then you will get a normal force and an axial force. In wind tunnel measurements, for example, normal force and axial forces are easier to obtain, because you often may be mounting this body by using some kind of a sting, a rod-like structure from behind, and then there may be a balance which is mounted suitably, which can take the axial force and the normal force, but not the lift and drag directly. However, from the axial and normal force, you may get the lift and drag very comfortably. So these are the things one has to do in order to get things together. So, well, am I doing CFD? Doesn't appear to be like that at this point. Okay, but I got very interested with what Professor Alam was showing yesterday, and I also thought that maybe some of it could be interesting for you. So, the attached flow and the separated flow. So this is some smoke flow visualization. You see, the lines seem to be attached for some distance, and there seems to be a separation, right? And this is mounted somewhere here inside the wind tunnel. This is a low speed wind tunnel, in which we have performed smoke flow visualization by having a rake through which smoke is injected from different points and so on. Very similar to what you saw yesterday. And then if you want to do a particle image velocimetry, then you could actually illuminate a plane, say the mid plane of that wing, because this wing spans from one end of the wind tunnel to the other, the side width of the wind tunnel. And then here is the airfoil. You see, this is one part of the airfoil on one end. There is the other part on the other end which is not visible, and the mid span part is where the laser sheet has been put. And then you put some seeding particles and so on, some fog, mist, etc. And then you run a PIV, you will see something like this. The PIV gives you some velocity vectors where clearly the separation region is identified. Okay. So that's how we can actually have a physical look at the flow field. We computed it earlier, and then we can try doing experiments and match. We are never sure whether our computations are good enough until unless we get a fair match between this and what the computations yielded. I don't have enough data here to show you the one-to-one match, because this was a different airfoil we did. That was a different airfoil on which we did CFD. But I'm just trying to send this message across to you, that under the same roof we should be looking at both the things hand in hand. It cannot be an isolated activity. Okay. So more on it. So there are regimes where you might have nice looking attached flow because the angle of attack is low, and then there are regimes where you have separated flow, just like what we saw some time back. And then this is some kind of a time averaged picture, because the moment the flow separates, it becomes unsteady. Okay, continuously the flow structures over there are evolving. For example, the CFD that we saw over here, it's not a steady feature. That means if you keep looking at it over time, it's not going to look like that. It's going to continuously evolve. All these vortex structures are going to change with time. Okay, some of them will leave the scene, fresh ones will get generated, they will keep moving around, and so much. That means this is basically an instantaneous picture. However, if you acquire them over a long time and you do some kind of an averaging, then you get pictures of this kind. So it's some kind of a time averaging of spatial data which gives you these kind of pictures, while the temporal history looks quite different. See, these are instantaneous pictures which are continuously changing. So when you do the CFD will also hopefully keep predicting different pictures at different time instants. If you allow enough time to look at the pictures, not very short time intervals, but maybe a sizable time limit, then you will see the flow's evolution with time. And often these phenomena go on and on and on. They will never become steady asymptotically. They will remain unsteady. They reach a certain saturation state and they keep behaving like that in that manner. Okay. So this has something to do with even nonlinear dynamics. We are not getting into that. So that's how things look like, and that's how we need to compare between your CAFD and experiments, and PIV happens to be a very nice visualization tool. And the nice thing is that if you are able to do the experiment with reasonable rigor, you will get really good reliable data. One very important catch is that you are seeding the flow, right? You are putting in some mist, some what should I say, droplets, right, which can shine when you put that laser sheet. Now, how do you know that those droplets are not heavy enough that they will start settling as they flow? So they need to be neutrally buoyant. All right, so they need to be almost at the same density on an average with the surrounding air. Only then they will not drop. So that's one of the things. The other thing is that they should have nice reflecting property. Only then they will shine when you have the laser sheet illuminating it. Okay, and the PIV, the deep inside, what the algorithm is doing is it's tracking those spots, the illuminated spots, as a time sequence, and then trying to build the velocity vectors. Right. Let's look at another problem. So this is case study 2. Okay, a very classical problem. I mean, something similar to what Professor Shen was talking about yesterday. So it's a flow past a circular cylinder here. We can talk about other geometries also at low and moderate Reynolds numbers. And he told you very elaborately why the flow may turn 3D beyond a Reynolds number of this range and so on. So this is typically the kind of domain we define for this problem, and then we try to scale all these dimensions, domain dimensions, usually in terms of the characteristic length of the body, which is the diameter of the cylinder, and then define this as upstream, inflow, downstream, outflow, and so on. And if you are doing an unconfined flow, then all these are like far field conditions, far field boundaries, where you basically ensure that you don't have any kind of shear acting on those boundaries. Otherwise, if it is a internal flow, it may be a flow through a pipe in which you have put the cylinder, then it's a completely contained flow, internal flow. If it is the car body kind of situation, then this should come closer to the wall, and then this becomes a fixed wall or a moving wall. So naturally the geometry of the body, the dimensions scaled with the geometry of the body, then the proximity of the body with respect to a possible wall, the boundary conditions that you impose, except all these important things, each one of the aspects have to be done with care. And finally, you also have to take a call that what kind of Reynolds numbers are you choosing to simulate, and then whether you can actually do with a 2D or a 3D domain. So this problem is very well studied already. That's why we know a priori the kind of Reynolds number ranges where it effectively acts like a 2D, and then beyond it acts like 3D. So in such problems you have a distinct advantage that the problem has been studied extensively. However, it may not be all that comfortable all the time. For example, a new car design, where has that been studied before? Nobody has studied that before, right? So the pressure distribution, skin friction, wake, everything will turn out to be somewhat different from existing data, and that's one of the reasons why the car companies are desperate in bringing out a new configuration with new characteristics, new features, so that it sells, right? So there you do not have exact confirmation that this works or that works. However, this is a well studied problem, and therefore you know that these things work, and we just tried simulating it for a Reynolds number of about 500 or so, which is still low Reynolds number, I would consider. Later on we'll look at a little more here and there in terms of the Reynolds number range. I don't know whether this works. Let me try from here. Yeah. Well, so yeah, this is again colorful fluid dynamics and all that. Yeah, in action. So my PhD scholar, he's a Prime Minister Research Fellow, Mr. Ribhupal, he was kind enough to simulate all this for me just 3 days back, and we did it with open foam, the pimple foam, package, and here we use a pressure velocity coupling which is based on what is called as a simple algorithm. This is a well known, widely used algorithm for coupling pressure velocity fields. Earlier you remember we talked about why that coupling is required, because apparently the continuity and the momentum equation has a kind of a disconnection. Okay, there is no single dependent variable which runs through all the equations, and that's where the problem is. We don't face that problem in compressible Navier-Stokes equation because density makes its way through all the equations. Okay, and then we have a nice coupling. Okay, unfortunately the contours seem to be a little hazy, but excuse me for that. Here we are talking about 500 Reynolds number. The Lx is basically the xy's length 55 times this diameter, but usually longer domains are often taken so that the boundary conditions influence the dynamics of the flow to a lesser and lesser extent, and improved boundary conditions which can be imposed on shorter domains remains a research topic till date. And then you have all the dimensional details, and remember this is a 3D simulation. It has 20 times the d in the z direction, which is not visible here. You know, it's in the out of the plane of this paper. You have a 20 times d. Now it's obvious that if that dynamics goes on and on and on, there's some kind of a cyclic variation, you know, in the flow features, and that will kind of intuitively we can understand that there will be cyclic variations of forces. Lift or drag, it generally will have some kind of a time variation, and usually that's expected to be cyclic. Here we already know that 500 Reynolds number means it's already turned 3D. Maybe there's a little bit of turbulence coming in, so we haven't tried modeling the turbulence in any way. We did a direct numerical simulation. What that basically means is we are neither time averaging nor we are using a spatial filter, so we are not taking those runs or LES approaches. We are just trying to compute all of the turbulence content, whatever it is, directly by solving the Navier-Stokes equations. What do you need to have for ensuring that you are effectively doing it? You need to have a fine enough mesh, you need to have a small enough time step, you need to have high accuracy schemes which resolve the features of the flow. So there comes the convective terms discretization. You remember the non-linear advective or convective term on the left hand side of the Navier-Stokes equation, the momentum equation, that's how it is discretized. We looked at first order, second order accuracy, right, in our finite difference method part. Here we are talking about fourth order, if it is central, or third order upwind. Remember, when it was upwind, that is either forward or backward differencing, it was first order. That means the order was odd, 1, 3, 5. That's how it's going to go on. Okay. While if it is symmetric, it's going to be second order. We saw second order, but we could go to fourth, sixth, eighth, and so on. So here it's like fourth if it is operating as central. It's third if it is operating as upwind. The other way of looking at it is you start from fourth order central and you add a little bit of numerical viscosity, and that would basically turn it into a third order scheme. That's a different angle altogether. Okay, so that's the advection or convection term. The diffusion and gradient terms, those are discretized using fourth order central again. Okay, usually the terms, the viscous force terms, are discretized using central differencing because they don't have a directional bias. Why is it? Because it's molecular viscosity which is the playing the role of momentum diffusion, which doesn't have a directionality involved in it. Is it not? It's random. It works equally on all directions. So the numerical scheme also should not artificially bias it in any direction. That's basically the reason why it should be central. The other thing is the time stepping. So we use Crank-Nicholson, which is called as a semi-implicit time stepping. The advantage is, you remember, implicit time stepping doesn't have a stability constraint. What does that mean? Without destabilizing the computations, you can choose delta t values which are rather high and march the solution rather rapidly, and even then the solutions will not become unstable numerically. Okay, the flip side of that coin is, if you choose large delta t, you may be missing valuable information in between, because you are stepping too rapidly to catch the details in terms of a time sequence. So you have to take a call that what should be your delta t so that your physics gets captured well. Again, it's not too small because it's restricted by stability constraints. So the implicit schemes give you that kind of freedom to choose between the stability issue and the issue related to the the time wise details that you would like to resolve. Okay, so you have the freedom to choose. For example, here we have tried CFL numbers of the order of 10, okay, which basically means that the flow can step 10 cells, okay, for every delta t, every small time interval that you cross, which is quite a bit, but even then it did not destabilize. But then we brought it down considerably, because that would take out the nice details in the time domain, and therefore what is the consequence? The consequence will be seen, for example, if you do a Fourier transform, okay, then you will find that the frequency peaks are not coming out well. Why? Because you have a very coarse time wise resolution. So those are the impacts you have to be careful about. Okay, let's leave this and go to the next. So I was talking about this. So this is typically the turbulent kinetic energy spectrum, okay, and on the bottom what you have is basically a non-dimensional frequency, okay, we say Strouhal number. That's nothing but frequency in a non-dimensional sense. It's ranging over say from a very small value of the order of fraction of 1 or something to few hundred, and the energy spectrum that we see is dipping down with some a kind of peaks over here which are rather discrete, which is the low frequency part of it and probably has some connection with the vortex shedding, to a broadband part which is down below. So there are these larger scales here associated with lower frequencies, and the smaller scales here which is absolutely related to the turbulence, and also some intermediate scales, and they say that energy is percolating all the way from here to these levels. All right, and also the turbulent kinetic energy monotonically decreases as you move downhill from here to here. The energy that is fed in from here, this side, is actually dumped here. The energy comes basically from inviscid mechanisms. So this is a very quick overview of what the interpretation is all about. Now why I said that this is very relevant is because this has a connection to the quality of resolution that you have. If you had a kind of a straight line here without much of these ripples, then you might interpret it this way, that possibly quite a bit of the small scale phenomena has not been captured at all. It has been filtered out somehow or the other. It may be because of the limitation of the numerical scheme, or it may be some kind of a filtering approach that you are applying to solve the equations, if it is some kind of a LES or something, or there may be some other problem, or at a much lower Reynolds number where the flow is not at all turbulent, then you might have a flatter line here. You may not have a broadband structure here because this has a connection with the turbulent nature of the flow. So there are a lot of interpretations one can do over here, and then on top we have something a little more weird. It looks more like skeletons. What has that got to do with the flow? It's a very strange thing we are seeing here. Nothing to do with lift, nothing to do with the drag, pressure, nothing. So what is this? This is rather strange. So what that is some kind of a modal decomposition of the flow. Okay, so we have a lot of information here, a lot of grid points, a lot of spatial temporal variations going on in all those grid points. So you have spatio-temporal information which is in so-called higher dimensional space. Okay, you could have a way of representing that as a series in such a manner that the first term in that series will pick up the most dynamically relevant mode which is embedded in the flow. All right, with its corresponding frequency and its growth or decay rate. All right. So the mode 1 is basically that one. Okay. Then comes the mode 2, then comes the higher modes and so on. So effectively you are trying to represent that dynamics from a very large high dimensional space to a correspondingly lower dimensional space where the same kind of information with a little bit of inaccuracy may be represented in the form of a combined representation of a few modes in a summative manner. All right, and there is more information associated with it. I have just shown you the spatial nature of the modes. That is a kind of a skeleton of the flow, what's going on deep inside. There are deep structures embedded inside this so-called naive flow. You know, when you run this, you don't get to see that, but deep inside all that is going on. Okay, so around the car body, when you do the CFD, you will see some features. If you do a dynamic mode decomposition of that, you will see the skeleton of the flow, layers of skeletons summed up over and over and over again, maybe 100 of them, and then you see the actual flow field. Very near to the actual solution, this reconstructed flow field will have a kind of close parity, close similarity. Okay, that's the whole magic here. Now what have we gained in the process? We are talking about a very complex phenomena, right? We are saying that, well, we can kind of rebuild or reconstruct that phenomena using a few number of modes with their structures, the spatial structures, and the corresponding frequency information and growth and decay rate information and so on. Unfortunately, I forgot to put this aspect. There is a plot which we generally do. It looks more like a circle, and that circle, there are points inside the circle, points on the circle and beyond, and where they are basically decides whether it's stable, it's decaying, or it's growing. Okay, if it is on the circumference of the circle, it's a stable mode, it will remain that way. If it is beyond, it will become unstable. If it is inside, it will get damped, so it will vanish after a while if it is damped. So dynamic mode decomposition is extremely elegant. You can try looking at this later. Okay, so how it will fit into your car aerodynamics is something that your generation needs to explore. I am not the person to do that, because, you know, as Professor Alam said, we are getting old. Okay, so you have to take on, you have to take the baton and explore all this. Now similar things were done on other studies. I mean, here there is a slightly different approach that we follow. This is also a modal decomposition technique which we call as POD, proper orthogonal decomposition. There we don't look at the dynamics, but we look at the energy content of modes. All right, we can arrange them in order of reducing energy content, and then what you end up having is the proper orthogonal decomposition modal structures, and you see they have temporal variation. So here we associate the spatial structures with their temporal variation. So this may look a little weird in the sense, what connection does it have with our car aerodynamics? I am not saying it has a very apparent connection, but I am just saying that all the time we said that we need to understand the physics better and better and better to an in-depth level. Who knows whether these may come in handy for you? Let's say you make a slight change in the shape, or you are applying some kind of a small control mechanism, maybe a small vortex generator. What will that do to the wake of the body? What will that do to flow structures in the neighborhood of some features on the car? You can do a DMD or a POD and they will answer you what has happened. And they will also answer you that in order to reach a desired goal, how you need to control the features, shape or size to some extent, if you can make it a kind of a looped activity like that, a feedback. Okay, so these are very interesting things you can explore, and we did a bit of exploration, and some of it is reported in a paper which was written almost 10 years back. So I thank Dr. Supradipan, who is currently working in BITS Pilani, Hyderabad campus, who was responsible for this work. He also explored with, I don't know whether you can see that, you know, side-by-side configurations and things like that, all the fancy stuff we do in bluff body aerodynamics. We love doing that, and we love watching these funny wakes and so on. And then we found that if we place them close enough, then the nice looking periodic forces and all, they become so erratic. Apparently turning from a periodic regime to a mildly aperiodic regime and gradually to a chaotic regime. And there are ways of evaluating the level or degree of chaos which exists. So we did some quantitative assessments of that, and we did find that for some ranges it actually turns completely chaotic. Okay, so this is another part of blood body aerodynamics. Again, we did POD and all that, and here we did a bit of phase portrait. I think Professor Shen was talking about phase portraits yesterday, and you would be amazed to see how these phase portraits dramatically change from a periodic regime to a mildly aperiodic regime and a completely chaotic regime. This is typically something that may happen in a somewhat aperiodic, mildly chaotic regime. And this is a plot typically what explains that there is reducing energy content of the modes that we are talking about. You are moving downhill here. The first mode contains the largest energy, the second mode a little lesser, the third mode still little lesser, and you may often see them in step-like structures because they turn out to be complex conjugates. Okay, so this is the first mode, the second mode. How interesting they look like. They don't have a direct connection with the common vortex street, but they seem to be carrying the energy in lobe-like structures. So interesting. Okay, so you are creating lobes without even knowing that lobes are hidden inside the flow. And then the higher modes and so on. And this is how they vary over time. More stuff, some fancy stuff. This has a little bit of connection with what we discussed, that you have a little bit of a shear imposed because this is a solid wall. So this is a block body close to a ground, and therefore you cannot have a uniform flow here. There has to be some kind of a shear imposed on the flow because there is going to be a boundary layer. Here the ground is fixed. So imagine that these cylinders are put into your wind tunnel. Then what will happen if the bottom wall is a fixed one? The flow will approach from upstream, and then as it approaches, it will develop a boundary layer character, right? And then it comes and meets these bodies, and probably behind the body you'll have all the common vortex street interaction and so on going on. So that's what has been simulated here. And then again we tried to do all those modal decomposition, and we saw very interestingly that the moment you bring in this wall, the modal structures also get so much more distorted because there is interference now between the structures and the wall. There comes your wall effect. I'm sure that if you make this ground to move, then the modes will definitely see a change again. Therefore, when we test a ground vehicle in proximity of a wind tunnel wall, which is on one hand fixed, on another it is moving, definitely there is going to be some change, but I am not very sure how much it reflects on your drag and lift. But in terms of flow structures, it doesn't, it goes without saying that there is going to be some change. Alright, so here we just showed that picture just to bring in the matter of asymmetry which is setting into the modal structures. If you go back and if you were looking at a body like this in unconfined flow, see, they seem to be kind of symmetric about this axis. It's clear. Again, you might say that, well, there is cylinder to cylinder interference. Yes, that does have an effect, but additionally the ground would also have an effect. And there is more to this over here, and how much the gap change would influence the flow structure and so on. So that's that, more or less done. A lot of colors again. So what is this? We have moved from a smooth bluff body to a one which has corners. Now the aerodynamics has a dramatic change here. On a smooth surface, the separation points are not known a priori. It depends on the Reynolds number, it depends on the surface roughness, it depends on free stream turbulence, so many things. And then accordingly the separation point on a circular cylinder gets decided. You cannot define it a priori, and Navier-Stokes will automatically capture that. You don't have to dictate it to the Navier-Stokes solution. While if you bring in a body like this, say it's like a building structure or a block body block or whatever, it has sharp corners, right? Now when the flow goes and meets such sharp corners, it can manage to stick to the surface only if it is accelerating substantially, because there is an abrupt change in direction and so on, which a viscous flow generally doesn't manage to achieve, and thereby it finally leads to a separation of the flow. I am not very sure how clear that is, where we have tried to mark with two different colors the opposite families of vortices, the clockwise and counterclockwise ones. The important message is that yes, when the flow turns three-dimensional, you can see clear changes in the span-wise direction. That's why I just hurriedly put these figures in, just to make sure that Professor Shen's predictions are so very true. That yes, I mean, once the Reynolds number goes up, and this is not much, this is just 200, and we did it with some in-house solver. So clearly things are changing in the other direction. Okay, and if you have a plan view of what's going on here, you see the structures here advecting. This is the cylinder basically, and these are the structures advecting down. Okay, so this is a very important bit of information we need to remember. The flow separates from corners. Yesterday when Professor Alam was showing us some simplified car geometries to do the tough flow visualization and things like that, he clearly mentioned that to simplify the geometry and begin the whole investigation, you start that way, where you will have very dramatic corners, in the models, in the simplified models, and they will obviously lead to such things, dramatic separations, larger drag and so on. Later on you realize that you have to round off the things, make them much smoother, and then help the flow to remain attached as far as possible, which will obviously lead to a lower drag, a lower momentum crisis in the wake and so on. So these kind of studies point out very clearly the directions in which you need to think, that you have to avoid sharp corners. That's clean and cut, and for vehicle aerodynamics that needs to be followed. Okay, so again some other geometries like a wedge and so on, and a couple of more cylinders, different kinds of flow patterns. There were some papers where we reported all this. One thing that I would like to say is that when you have a large number of them, usually you can have a cluster of them, say in nuclear power plants, in cooling rods and so on. So there, if you have a large number of them in close proximity, the problem is if you try forcing a structured grid into that kind of a situation, it becomes a hell of a job to get it done. Normally we prefer doing an unstructured grid over here, but you have to have very good control over the grid resolution so that you don't unknowingly or knowingly damp the flow features, otherwise your predictions can go wrong. Okay, so we move on to another study. This is a very old problem. We were just re-looking at it. I was visiting some lab abroad, and then we decided to have a re-look. That's it. We didn't want to do anything new, neither we had the guts of doing anything new, because there were stalwarts who had already looked at this. But we were just trying to investigate this, that well, if we do numerical simulations, can we come close to this? And that's how we started doing it. And you all know that there's what is called as a subcritical flow and supercritical flow, in the circular cylinder flow. And if you go to the supercritical regime, you have a dramatically reduced width of the wake of the cylinder, because the separation point, the separation gets delayed significantly, because probably there's some formation of a laminar separation bubble. Once your laminar boundary layer separates, it undergoes transition in the shear layer, it reattaches, and then you have a completely turbulent boundary layer which separates much later, because it's more robust, it has more momentum content in it and so on. And what is the consequence? The dramatic consequence is this: from 1.2 it may come down to 0.7. So we just tried to look at it, and we were anticipating that literature was showing all this, that people like Achenbach and Roshko, the stalwarts, they have already done studies on this. They showed that the red color curve, which we learned from potential flow theory, the 1 minus 4 sine square theta thing, how far are we from that? Because if we were to follow this identically, we would have no drag, D'Alembert's, right? D'Alembert's paradox, that's what we say, no drag at all. So can we go anywhere close to that? No, may not be, but if this happens, then maybe if subcritical shows something like this, the supercritical may be dipping much lower, all right, and whether the CFD can actually go about capturing it. And we had a good look at all this, which comes from classical literature, where we have from Roshko, in the book of Schlichting, which many of you may have read or have started reading on boundary layer theory, and many other very good pieces of work down the line, starting from way back in the 1920s and stretching way into the recent times, where Zrabko, which is book which is published in the late 90s, has again categorized all the flow regimes. We were talking about this book yesterday, in fact, with Dr. Shen and others, and then we started looking at the recent papers, and we just gave it a thought whether it's worth trying to simulate this problem. Okay, that would also show whether the numerical tools can do a good job in predicting this. So we studied from the literature that they said that in the subcritical regime, the boundary layer undergoes laminar separation and the mean drag coefficient remains almost constant with increase in Reynolds number. The wake is relatively wide. While in the critical regime, the boundary layer is laminar when it first separates from the surface and then undergoes transition to a turbulent state and reattaches. It separates at the turbulent boundary layer further downstream and so on. And they also talk about laminar separation bubble formation. And some of the recent literature they are also indicating towards either a one bubble on one side, no bubble on the other, or two bubbles simultaneously, and so on. And in supercritical regime, the CD increases with increasing Reynolds number and so on. So we had our collaborators here in Germany. I was visiting them, and they have a very nice flow solver which is based on lattice-Boltzmann. They solve Navier-Stokes equation using lattice-Boltzmann, and we picked a Reynolds number of the order of 300,000. Okay, we just gave it a try. Okay, let's see what happens. And then when we gave it a try, then this is what we noticed. I have just started running the left one. Okay, and we saw very interestingly that yes, there was some trouble with the boundary layer, but which is at a much larger theta than usual, because the theta separation at comparatively lower Reynolds number are way high up there. You are just seeing one part of the rear cylinder, rear portion of the cylinder. You can imagine that the center lies, somewhere deep there, and here is the curvature. It's basically this part of the cylinder, right? So you can figure out that it's happening somewhere here. Okay, and we did time averaging, etc., and we interestingly saw that in the pressure coefficient plot, there was a funny kink coming somewhere downstream. Okay, so there's an oscillation coming here. I'm not going into the details, but I'm just showing you some indication that what was going on there. And we looked at nitty-gritties of the flow, and that research is still on. So maybe in some time, if we are able to take it to a certain level, I'll get back to you. Okay, so here if you look at the entire flow, then it looks somewhat like this. So you see the structures here, and it's way below. It's a narrow wake. This is not the usual thick, wide wake. Okay, so it's a much truncated tail like structure. So that's what was going on, but it's all very nice fun here. But if you want to extract a lot of useful information, sometimes it could be challenging. We tried doing it. We are still trying in some way. So let's see where it goes later, but I just wanted to show you this, that cylinder flow doesn't look the same over the entire range of Reynolds numbers. There could be dramatic differences. Okay. Now imagine that same cylinder, because it's obviously a three-dimensional simulation, you can imagine it has some span-wise dimension. Okay, so the cylinder basically is like this. This is the angle from which we are looking. This is the cylinder. Okay, so this is the surface of the cylinder, the upper surface, that is the lower surface, and we are trying to plot that funny thing Q criterion. I talked about it some time back in order to capture the coherent structures. So now if you look at what's going on, oh I'm sorry, just give me a minute. Now if you try to look at this, what happens? You see this. So the separation has started somewhere here, and you know, these are the structures which are moving down. This is a very close up view of what's going on in the span-wise direction. So there's a lot of physics here. So young people here, it's up to you to look at this physics, go deep into this, and then probably tomorrow we have a chance of understanding block body flows better. Okay, and then probably our vehicle designs etc. will improve that much more if we go deep into this physics and we know how to control it, how to make it flow the way we want, and that's where the magic lies. If we can do that, then I think things will work better tomorrow. Okay, just for the excitement of it, I'll run it one more time. Yeah. Okay, I'm very much thankful to my collaborators for giving me this opportunity. And then if you want to understand more of this, you have to do a lot of hard work. Okay, so hard work, one part of the hard work is going through all that has been published till date, all that has been understood and reported. That is one very important part of the hard work. Okay, so there are a lot of papers related to this area. Quite a few here are in the connection of laminar separation bubble, which I talked about. Quite a few experiments, quite a few numerical simulations, and as applied to bluff bodies as well as streamlined bodies put together so that we have a more unified understanding of what's going on for different geometry changes. I'm not detailing on this because I don't think that will add much value to our discussion, but I'll share the slides with you later, so probably you'll be able to read through all this, and get more information. This is an excerpt from this book. This is a very classical book, all of us we know. I've taken a little material out of it from the 9th edition. It's one of the more recent editions. So it's Schlichting's boundary layer theory, 9th edition, chapter 15, onset of turbulence and all that. They have made some plots here, and what they are trying to say is kind of summed up here. I'll just read through the lines for your convenience. So it says, well, before I read through, you see what they have drawn. They have a flat plate here, there's a boundary layer, and then there is a Kalman vortex shedding here behind the cylinder, and they have tried marking some zones now. If the cylinder is somewhere here, and then they have tried marking some zones behind the cylinder, in and around in the wake and so on. So what are they trying to say here? Let's see. So they say temporal and spatial amplification of disturbance in a transitional flow field require the absolutely unstable or absolutely sensitive regions to be determined. So what they are talking about essentially is that how will the disturbances grow with time and propagate in the domain, okay, when you have a cylinder sitting out there in the flow. It turned out that precisely these regions of the flow field are of particular importance for the laminar turbulent transition and efficient ways of controlling it. So it's not only watching, but perhaps also trying to control it. So if you have a fair understanding of what's going on here, only then do you have a chance of controlling it. So fluid mechanical instabilities which commence abruptly, as in the wake flow behind a body, are absolutely unstable. We define an absolutely unstable region to be that flow region where perturbations added locally are magnified temporally and spatially, and with increasing time affect the entire absolutely unstable flow region. In convectively unstable regions, locally introduced perturbations flow downstream and can at later times no longer affect the original position of the perturbation. That means they will just make their way downstream, they cannot come back and influence upstream. The instabilities of the plate boundary layer which lead to the turbulent boundary layer via several discrete instabilities are convectively unstable. This determines a division of areas of viscous flows with the basics of stability analysis, one which also differentiates between flow regimes of absolute and convective instability, about the indifference of Reynolds number, and so on. Now, why this slide is put over here is just to draw your attention to this aspect, that we have to finally consider all these things from an instability angle. Okay, so how do the instabilities get generated? How do they grow over time and space? Whether they have a preferential direction of propagation or they do not have any directional dependence? What kinds of instabilities may be involved in this whole process? That has a lot to do with how the flow actually evolves around a block body. Okay, so this is another angle. Like we saw one possible angle of looking at the modal decomposition. That is one angle. This is another angle from where you look at the stability of the flow. All right. As you all know that there are standard means of doing stability analysis. If you were to use what we call as Orr-Sommerfeld equations and things like that, stability is perceived from the linear stability angle. But here the kind of flows which are produced for block bodies, you can look at onset of instability, that I understand, but probably that won't be sufficient to understand when it is already into a vortex shedding kind of a regime. This is fourth case study, all right, and I'm sorry, this looks a little dark and not too attractive. Let me go to a later picture and then you will understand what that is all about. Okay, so none of them are so very clean, but okay, let me have a brief on this. What we have is a thin flat plate, okay, of not significant aspect ratio. That means it doesn't have much width, okay, it has a certain chord length and then has some moderate width, and then you are holding it from its root and you are trying to pitch it up and down. So this is that plate, you are holding it at its root and there is a mechanism which can make it pitch up and down, up and down. Okay, so what does it produce? It produces a kind of a flapping of that plate. Okay, so the plate is flapping by means of that mechanism. What has it got to do with block body flows? Again, the way it is pitching will produce large scale separation, which is also seen behind block bodies. If the flow was nicely streamlined with the plate, it would have never occurred, but here it would occur that way. What is the proof of that? You see separation here. Here is the plate. It is an instantaneous snapshot of the flow. So this plate is probably moving down at this point, okay, and it has been instantaneously captured. The flow field has been captured by means of what? By means of this setup. It's a PIV setup. Okay, so what has been done basically is there is this small thing sitting out there inside this box like thing. What is that box? It's basically a container with perspex sheets all around, so it has optical access, all right, and then we have filled water in it. Okay, and then after filling water, what we have done is we have put micron level glass globules, okay, with some kind of coating which is nicely reflective, and the glass globule size is such that it's also neutrally buoyant in water, which is a essential requirement for doing PIV. Okay, so in this box you put in this mechanism which holds that plate. That mechanism is basically a rocking mechanism kind of. Okay, so you have studied about machines and mechanism, linkages and all that. So all that is there. What that produces is flapping of that plate. What's the motivation behind doing this? Well, such things may be applied in small vehicles which may be operating underwater. Okay, there's a lot of work going on in underwater vehicles these days. Okay, that's a different, sorry, that's a different segment of vehicles, but that's also transportation in some way. All right. You may also conceive such vehicles as small flying ones deploying flapping wings. The way it is flapping here, however, may not propel it very effectively, because it's just flapping up and down, up and down. But if you do that in an asymmetric manner, that means about the horizontal orientation, if you have a little more sweep on one side compared to the other, then probably in a time average manner you will have a net force which will keep it floating. That is what is called as hovering, as we say. Okay, so we are not propelling ahead, but we are just trying to hover. If you have that in mind, then this works. If you want to churn some fluid, let's say in chemical and process industries, we may like to do such things. Okay, so if churning is done, how does the flow behave around a surface like this? Producing large scale separation, which may help in mixing. Okay, so bluff body aerodynamics also helps mixing. Bluff body aerodynamics also helps operate underwater vehicles which are deploying flapping surfaces. All right, so that's the point. So there are many other things in the neighborhood which help you do that study. So in brief, if you try to look at it, so you have cameras sitting out here. They are looking at the flow field. When will they be able to look effectively at the flow field? When there is a laser shot coming from here. So once the room is made completely dark, so that there is no light coming from external sources, then there is a laser unit which is here, which will start shooting laser sheets towards that small plate, and the laser sheet exactly cuts through the mid span of that plate, so that you are not close to the edges of the plate, the lateral edges of the plate. Okay, so when you do that and you perform the PIV, then the velocity vectors would come out like this. Now there's more to this, because when the laser shot comes out, immediately these cameras have to respond, because you light up that region and the camera opens to take a shot. Okay, and then what does the camera acquire? It acquires something like this. Here it appears all dark practically, only the mechanism is somewhat lighted up. But if I were to show you with increasing resolution, there are a lot of dots here which are mildly illuminated. So what are those dots? Those are those floating globules, glass globules, which are extremely tiny. Okay, and when the laser sheet illuminates them, then they show up as some bright spots here and there, and the whole setup is acquiring those shots in a sequence, and they will be lined up one after the other to finally rebuild this information in the form of velocity vectors. All right, so that's basically what we do in a PIV setup for a flapping wing. And here is a synchronizer, which is a very important unit in order to synchronize this laser shot and the opening and closing of the camera. So the synchronizer tells both the units when they should in a coordinated way operate, so that from time to time you illuminate, acquire, and then again make it dark in between. And up there you have some arrangement to take care of measurement of loads which are working on the flapping plate, because as it moves there are going to be forces created. And as Professor Firoz was telling yesterday, we are working with water which is 800 times heavier than air. It's not a light fluid. So there are also significant amount of inertial effects which are involved, right? So that you have to take into account. Okay, so we call it as added mass effect when we do such studies. So you have to take care of all that, and then you come out with even information about how the forces are varying and so on. So back to this, in the first slide that we tried to show, all this information was embedded, but it was not clear what was going on here. That's why I thought that it should be better done if we go back to a few slides later and then come back here. And what we ended up doing over here was we acquired such PIV images showing the velocity vectors. We also did some calculations to obtain the vorticity out of it that you can do. You know that if you take the curl of the velocity vector, you can get the vorticity out of it, right? So if you have the velocity vector information, then the curl can be obtained. And here we bother basically about only one component of vorticity, that is the omega z, as we say, okay, because it's apparently a planar image that we are taking. This is a limitation of the study in the sense that you may imagine that if you flap a plate like this with finite edges, then it's basically a three-dimensional flow, right? Because flow will roll up from the edges. So how come we are going to take just a two-dimensional picture of it and get away? Well, this is a poor man's experiment. Okay, we don't have a 3D volumetric PIV, and therefore instead of doing nothing, we thought that let's do it at midspan. Okay, and let's see what happens. So we captured some structures, but if you go closer to the edges of the wing, then the flow will roll up from the high pressure to the low pressure side, and the high pressure and low pressure will keep alternating depending on the stroke, whether it's downstroke or upstroke. Okay, whichever direction you are moving towards, you have a higher pressure on that side, lower pressure on the other. For example, if you were to look at this and it appears that it is shedding tip vortices here and so on, that means it is moving down, then you will have a higher pressure here compared to this side. And then when it goes down and starts coming up, then the upper surface will have a higher pressure than this, and the vortex will be shed down like this. That's how it goes on. Okay, so based on that, here we looked at the instantaneous snapshots, the PIV snapshots, the vorticity information, etc., and then we did a full 3D simulation. All right, and we then took a plane out of it which corresponds to that PIV plane, and we just compared the computed information for that plane and tried comparing the features. We got a reasonable match. I'm not saying we got excellent match, but there was reasonable match. We also tried to compute the CLCD data and compare with load cell data. So those were the things we did as far as the CFD is concerned, but in a planar sense you will not get the complete picture of the CFD unless I take you to this. Here you get a better feel of the 3D simulation. Here is that plate. When it flaps, you see extremely complicated structures are forming around the wing. Okay, so there is roll up from here, there is also roll up from here and there, so it's all wrapping around, and then you have a very complex vertical flow. And remember,
can you give the participant 5 minutes break?
Yes, we can, certainly. So it seems we need a 5 minutes break for some activity, so we'll just briefly break here and come back. Okay, thank you.
Hello.
এটার আপনার 10 মিনিট তো এটার উপর লাগবে
না বলে দিস
ওই তখন আচ্ছা
হ্যাঁ আমরা সামার তো 5 দিনের
হ্যাঁ সাম আচ্ছা কিন্তু এরা কি ফিরেছে সব ফিরেছে ओके तो आप थोड़ा ओके कीजिएगा ओके वेलकम बैक so we are heading towards the end here what we were talking about was a flow which is very rich in vortex structures around a three-dimensional oscillating plate and remember that it is oscillating in a quiescent medium. That means the fluid around it is not having any bulk direction of flow. So naturally the vortex structures that it creates, it stays on in its neighborhood and gradually dissipates because of viscous effects. But you would find their trace for a long time. If you were to move this with some velocity, then they would be advected naturally. Then we started looking at all these kind of getting deeper into investigating these flow structures, looking at the pressure distribution on the surface of the plate, etc. And then this simulation was not done with any in-house code. This was far more complicated, so we have used some solver from outside, and we had a tough time doing it because, as you can understand, this is a moving boundary problem. So we were talking about fluid structure interaction some time back, where a building under the wind load may be swinging a bit, and here it is a very vigorous movement of the plate, up and down, up and down. There's a lot of movement, and therefore in order to keep the mesh of fairly good quality around a moving body could be a big challenge. All that was addressed and solved in order to make sure that we were doing things correctly, we were getting reasonably good results and so on. So there was a lot of background effort which was put in by our scholars. So experiments were done by Srikanth, the analysis was done by Dr. Chakravarti and also by Dr. Srinath. So they are professionals, they are working in industry and academia. They also looked at a lot of diagnostic tools, these are some of the ones which you may also try exploring. So we did time series analysis, for example, that reveals a lot of information. We did phase space trajectories. Then recurrence quantification analysis is one of the tools which helps us in predicting the extent of chaoticness in a system. Okay. Then looking at the flow topology, okay, you can have interesting features like foci, saddle points, right? So you can there was a very interesting paper on all this topology of flows in Annual Review of Fluid Mechanics couple of decades back. So if you try to search through that paper, you will get to know a lot about that. So whenever you have such complex flows, you definitely need to look at what kind of flow topologies are created by the surrounding flow on the surface and also within the flow field. That reveals a lot of the physics of the flow. So that is associated with these singular points. All right. So that has to do with the flow topology. Bifurcation diagram, Professor Sen was talking about bifurcation phenomena yesterday, and then you could do some bifurcation analysis on flows of this kind and see whether it really happens for certain parametric regimes. The last one, FTLE, I am not going into details of this, but this has to do with what is called as Lagrangian coherent structures. Okay, so this helps us decipher the pockets of flow which are mixing with each other, pockets of flow which are kind of isolated from each other by following some kind of a Lagrangian approach. All right, so that is what is related to this FTLE thing. So if you search for FTLE or LCS, they will give you details of that. So I think we have kind of understood all of this. One time, I'm just going back. So the students were very enthusiastic. So they said that if we have done with a flat plate, we are also interested to see the effect of an appendage here, more like what we call as winglets. These days, if you are flying in these passenger aircrafts, you find that the wings are usually appended with fairly large winglets, you know, and that is what reduces your induced drag, as we say. All right, yes. So that is a kind of a, it tries to arrest or minimize the effect of the flow rolling up, and in the process tilting the lift vector and therefore creating drag out of it. So what happens if you deploy some kind of an appendage on a flapping structure like this, which was not reported ever in literature, and we saw that that acts more like a barrier and kinds of reshapes the vortex structures. So these are small learnings that we had through the study. Again, this is a PIV image only. Earlier we were looking at a fixed boundary, now we are looking at a moving boundary, and mind it, the students did a great job in doing this, because again doing PIV on a moving boundary was extremely difficult, but they managed to do it somehow. So we have done all this. I think it's time we can go back from here. The last one. Well, you may be wondering, what has it got to do with cars or industrial aerodynamics and vehicle aerodynamics as we mean it here on ground vehicles and so on, because this is a very different regime altogether. But I just put it in as case study 5 because we are looking at bluff bodies. Bluff bodies also are of importance in high speed flows, and there are vehicles flying at high speeds, which is also part of vehicle aerodynamics after all. So when you try to put some small obstacles, bluff bodies on surfaces which face high speed flows, you are not just putting them out of your fancy. Okay, this is not an academic exercise or something like that. Incidentally, let's say the rockets that fly from Sriharikota, if you look at their external surface, mostly it is smooth, but you cannot prevent creating some small protrusions here and there. It's virtually ruled out. You cannot prevent that altogether. So if there are such protrusions which are on the clean surface, then once the supersonic flow comes in contact with it, because as the rocket speeds up, it goes into the supersonic and later hypersonic regime and so on, then what kind of flows would be produced? Are they going to be the same as the cylinder flows we were looking few minutes back? Probably not. First of all, in terms of computational fluid dynamics, the compressible forms of the equations come into feature. Okay, if you are looking at it from an inviscid angle, it will be compressible Euler, all right, and if it is Navier-Stokes, then it's compressible Navier-Stokes. Okay, there will be significant density variations, significant pressure variations. Those are an integral part of compressible aerodynamics. Additionally, you will have wave-like structures in the flow, like what we were talking about some time back when we were discussing hyperbolic equations. And there we had a very simple model equation that was linear advection, but when you solve Navier-Stokes or Euler, there are non-linear interactions which these equations can capture. All right, and that comes through that advection term. All right, and what basically happens is that waves do not propagate through the domain without interfering with each other. If it was a linear propagation, they would remain as they are without disturbing each other. But in a non-linear problem, they interact with each other. And when they coalesce, they produce shock waves. When they go apart, they produce expansion waves. And all that would influence these kind of high-speed flows. All right. So when you have a flat surface on which you mount a small obstacle, it's an obstruction to the flow. It ends up producing a shock wave. Okay, the flow looks more like this. So here is that obstacle sitting on a flat surface in the test section of a supersonic wind tunnel, and then such structures are produced. There is a shock wave which wraps around this body, and horseshoe vortices roll back, and there are complicated interactions if you go deep into this. All right. If you were to do an oil flow, Okay, so we use a mix of titanium dioxide and oleic acid and all that, spray it on the surface of the wind tunnel side plate, and then you mount this model, run the tunnel, take it out, and you see such things. What this is indicating is a footprint of all that has happened. The footprint comes up here. Okay, the base features will be showing up here, because you cannot see the three-dimensional features, but you can see how they impressed upon the oil flow the dots of oil that you had put over there, and they have been dragged around by the flow in general and influenced by the shock and other structures additionally. So that leaves the footprint here. Okay, and this body has been set at different yaw orientations. So this is head on to the incoming supersonic flow. This is at a slight yaw angle. This is at a higher yaw angle. What that does is that these structures, the shock structure, the vortex structure, all of them got skewed in the process the moment you introduced yaw. Why do you need to introduce yaw? Because the small things that you have to put on the surface just to accommodate certain components, etc., they may not always be perfectly aligned with the flow. Okay, or the body may be taking a tilt and a turn somehow as it moves up. All right, in that case the yaw effects are also important. When you have a slender body here instead of a bluff one, then you may call that as a fin. Such fins are seen on, say, missile bodies. Okay, so these kind of studies give you some idea that how the flow could be dramatically different if it becomes a high speed flow moving past a bluff body. What is this? This is a very classical problem in compressible aerodynamics, which has been solved using some in-house CFD code. It solves two-dimensional Euler equation, so it's inviscid flow, right? What is it solving? This is your computational domain in which at the bottom there is a block. It's a bluff body, all right, and these are all fluid boundaries that you see over here. You are allowing some supersonic flow to come in from here and then meet this block. So it starts from here. The time development of the flow starts from here. So here the flow has barely reached this body, and the moment it happens, the body responds by creating a shock, just like what you saw in the other example, but here it's 2D. All right, so the shock has started developing ahead of the body. The body is blunt, and therefore the shock is thrown out of the body. If the body was thin and slender, the shock might have come and sat on the body. But nevertheless, there is a strong wave here, unlike what you see in low speed flows, where there may be pressure rise and pressure fall, but all that happens smoothly. It doesn't leave a trace of a very strong compression wave ever. So from a mathematical perspective, we say that hyperbolic equations have characteristic like solutions, and characteristics, when they merge, then it gives rise to a shock. So essentially this front is because it has been formed because some characteristics have merged, and the hyperbolic equations are allowing those characteristics to form first of all. Now if you allow more time, because you are time marching the solution after all, then gradually the flow features start developing. So from here you come down here. So by that time this shock has reached the top wall. Oh, I made a mistake here. This is a solid wall. This is not a fluid wall. I'm sorry. So this is an inflow, this is an outflow which allows fluid in and out. This is a solid wall, that is a solid wall as well. So when that shock reaches the upper surface, it reflects back. All right. Then you move up here. It reflects and reaches this bluff body. Again it reflects back. Okay. As time moves on, this nice looking structure reaching the wall now starts developing a feature here. It is moving away with a small stem. That is what we call as a Mach stem. Okay, and then gradually even here the reflection which had earlier left from the outlet boundary is getting in, reaching the wall, reflecting back, reaching the wall, reflecting back, again a little bit of a Mach stem following here. So all that keeps developing over time. That means in CFD simulations, when you are doing unsteady or transient simulations, in flows of this kind, where the flow will start from the inflow and gradually reach the body, start interacting with the body, the features will also develop sequentially. If you look at the different snapshots taken at different instants of time, the flow will show up different features. Alright. After a lot of time, it reaches some kind of a steady state. I was talking about that convergence issue. You tell the solver, you stop somewhere, right? So probably you stop here because you don't see any more changes happening. When will any change happen here? If in case you are making changes at the inflow, suddenly you speed up the flow more, you will see a fresh set of waves generating here, and things are again changing over some time before it reaches another steady state, and things like that. Or if you were moving this body, vibrating it, then things would change with time, not otherwise. Another thing, because it's an inviscid simulation, the shock reaches all the way up to the wall. If it was a viscous simulation, the flow would start showing the viscous behavior near the wall. So for example, here there would be a boundary layer forming, and then if there is a shock forming and reaching out to the boundary layer, then it's a very complicated thing. There is something called as a shock boundary layer interaction. Okay, within the boundary layer what is happening is the flow is gradually slowing down, right, from supersonic condition right up to zero velocity at the wall. So somewhere in between it will reach a Mach 1 condition, sonic condition. So above the sonic condition, up to that the shock can percolate, but below the sonic line there will be no shock. Alright, that is one. Second thing is, because the shock is standing above that sonic line, there is a high pressure gradient across it, shocks are going to have very high pressure jumps across them. The pressure behind the shock is way larger than the pressure ahead, and that huge pressure gradient is felt by the boundary layer, because just above the sonic line the shock is still existing, and if the region of the boundary layer below the sonic line gets to feel that, then that subsonic region which is lying below will immediately respond to that high pressure gradient and separate off. Because in the subsonic regime, the disturbances can percolate upstream and downstream. They are not confined to only moving downstream, while disturbances above the sonic line, where it is supersonic, disturbances which are created downstream of the shock will never reach upstream of the shock. Such funny things happen in compressible flow. It's again buff body, because this is of course not a streamlined body, that is clear. So you expose a blunt object to a supersonic flow, such strange things happen. So this is in a compressible domain. Fortunately this will not happen to your car, thank God, okay, and will not be shocked to ride the car. But if things were moving at such speeds, then it's going to happen like that. So as I explained, that because we were doing Euler simulations, you got to see how an inviscid simulation looks, and I'm not talking about a viscous simulation here, because that would be fairly different from this. As I explained, that when the shock tries to impinge on the boundary layer, what catastrophic things can happen. Mind it, all practical vehicles go through these realities. Practical vehicles will not see a neat inviscid flow, by the way. Whatever you have mounted on your GSLV or SLV, whatever, that is going to create all those shock boundary layer interactions. And the more troubling part of it is that when the shock impinges on the boundary layer, it separates the flow below, and it also creates time dependent movement of the shock and the separated region. That means there will be time dependent loading of the structure, which can cause fatigue. Such thing can happen to a wing also, which is flying at transonic regime, okay, deep into the transonic regime. Alright, so such things are, you have to explore such things and read up a little bit more and understand. I am not going to expand more on that. Let's go to the next slide. We are almost there. So my PhD scholar, he did some more simulations. So here you can see a part of a triangular wedge, half wedge rather. Okay, we took half the domain and simulated it. About the axis of symmetry, horizontal axis of symmetry, only half of that triangular wedge has been taken here, and I am just showing the wake part of it. And then you can see some vortex-like structures like we see in common vortex sheet, but you see some additional curves and things like that which are troubling. All right, the weaker ones carry acoustic information. All right, while the stronger ones are strong pressure waves, shock waves. And this is a typical case of what we call as shock diffraction. Okay, so we have colleagues here who are authorities on this, like Professor Abhishek has worked extensively on such problems, and this is another such. So you have a square step, and if you allow the supersonic flow to cross it, again you see there is some kind of a vortex street, but then more features coming in here. That means this Mach number regime behaves quite differently from what we saw earlier. Okay, that's that. We are done with figures, we are done with videos, all that colorful fluid dynamics and all. We are almost there, we are ending it. So I just wanted to pose these questions. We looked at block bodies, streamlined bodies in connection with vehicle aerodynamics, tried to address the issue that yes, we have to understand all of the physics put together. What can we say about the flow field around some such geometries? What are the common and different features? I think you know a lot about that now. How can you compute the flow field? What model equations can you use, or would you like to use, and why? So we have tried addressing that. What are the steps to be followed for performing the computations? We have a fair idea: pre-processing, solver, post-processing, and so on. What do you expect to use the data for after the computations are done? I think there's a for missing here. That means what utility will you have of that data that you have generated? Millions of digits of data and all that. Is it going to make any sense? That's the question here. How do you assess whether your chosen geometry is meeting your expectations? This is more from a design perspective. So going back to that vehicle geometry, you were given the CAD model, you did your simulations. Is it giving you the expected CD, the stability and things like that? So from a practical perspective, after doing all this, have you reached the intended goal, or you need to iterate further on the design? And finally, after doing all this, taking all this trouble, is CFD useful in choosing or designing body geometries that would be aerodynamically efficient and therefore would reduce fuel cost, would be comparatively less detrimental to our atmosphere? What is your opinion and why? So all that would probably come from practice. You have to apply all these tools, but going back to the objectives of this course, we need to connect. We need to connect how it has a connection with energy security, with sustainable environment, and how does it also drive our economic prosperity. So here is your CFD and experiments which will probably have an outreach into all this, and that's where probably the intentions of this course would be best fulfilled if you can have that connection somewhere down the line. And that's all up to you, how you can take this venture forward. Some future directions, thoughts. Well, I mean, there's nothing sacrosanct about this, but I just put them arbitrarily as it came to my mind. So the other day, Professor Alam gave a very interesting thought. I think it was on the first day. I was watching the YouTube. He was talking about having a cluster of autonomous vehicles, forming a formation or something like that, and then trying to move on a highway. There has to be some kind of autonomy so that we don't, bump into each other and so on. There is formation road driving, if you call it that way. So that has to also do with some physics that we already understand. It's inspired by that, formation flying, wake capture, and so on. So this is something definitely which you should be looking at. Recently we did some work on that, and you could have a look at this paper which was published last year on wake aerodynamics of flapping systems in formation flight. We have just tried putting in some new ideas there. Just have a look if that helps you in some way, and whether that can connect with future prospective application of that physics here. Physics based interpretations of the flow around a vehicle, I think I have more than emphasized on that. Synergy between experiments and CFD for improved designs to meet future challenges, that also we have discussed. Here comes increased use of reduced order models during design cycles. You know, these days for quite some time there is this MDO paradigm, multidisciplinary optimization in industry. So we say that from aerospace, for example, we say that an aerodynamicist just looks at the aerodynamics, the propulsion person just looks at the power plant, the structure person just looks at the structure, the flight mechanics control person just looks at control and stability, but the design is all of it, and there are compromises to be made in order to reach your objective function, whatever it may be. So you have to have very effective kind of less time consuming processes that you can follow, so that you can iterate the design over and over again over a short period of time. So for that you need to look at reduced order models. Professor Alam showed us the direction from the experimental angle. Go for simplified geometries to begin with. That will give you a ballpark number to begin with, right? Then as the other groups in the car design unit gives their respective inputs, then you refine your design and so on. You may not have the final say all the time. You may have to make compromises here and there because they want it in some other way to accommodate part of the engine or transmission or maybe some other thing. They want to make the dicky longer or whatever it may be. Therefore, you have to have simplified geometries to begin with, to get rough estimates in the beginning, which will not consume much time to investigate and give you the numbers, and then you start making more accurate things towards the end. So reduced order modeling has to do with shorter time cycles, which is very important for design, all right, more from the multidisciplinary optimization perspective. That's what we call as MDO, and that may need simplified wind tunnel models, simplified CAD models for the CFD, and also I am emphasizing that this could come to some use, that we need to look at modal decomposition of flows where we approximate three-dimensional CFD simulation data in the form of much lower dimensional modal data, which nearly gives you the same result. In that case, you can play around with this tool and say that a little bit of design tweaking, what it did to the modes, because the modes would get changed to some extent here and there, and that will finally help you to get the prediction very quickly. Again, probably this will come in some way or the other. It's already coming in a big way. Physics based AI models. So integrate experiments, CFD findings for futuristic design of vehicles, buildings, wind turbines, bridges, where AI plays a role. AI also integrates data coming from experiments and CFD, merge them together, learn the physics out of it, and try to develop models which can do a good job in terms of predictions. So that even without very extensive investigations in a particular direction, AI may just show you some big ways, and then you may get into one of the ways and investigate more in a more detailed manner. So in that case, maybe AI will be helpful in some manner or the other. So I think with that I'll come to the end, and before I hand over the stage to the organizers, I would like to very sincerely thank the organizers for having given me the chance to come and share all this with you. I'm extremely indebted to the participating faculty, Professor Alam, Professor Shen, Professor Abhishek, Professor Paul and many others who are in the behind the scene, probably Professor Sahu and all, for having so nicely arranged this course, so well managed and so on. And I again thank my scholars, my past students, my collaborators for all the data that I have managed to show over here. A lot of hard work which has gone on behind the scene, which made this possible for me. Okay, I have very little contribution to what I showed here. The bulk of the contribution comes from my team. Okay, while if there are any mistakes I have committed, it's all my responsibility. Okay, with that I hand over the microphone to Professor Paul, and thank you once again.
So I would like to invite Professor Firoz to summarize the workshop. Tomorrow is the day for evaluation and feedback. So Professor Firoz, could you please summarize the workshop in few minutes, in 10 minutes, and take a informal feedback from our participants?
All right, thank you. Thank you. I think this is the formal part. We came the deliberation, and last 5 days you have gone through many things, many aspects of industrial and vehicle aerodynamics. Of course, within the time frame we could not cover everything, but we gave you some glimpse that what are the things you are going to face very soon, or some of you are already facing, and where you can make a significant contribution for the advancement of this very vital area of science. So and many things depends on your achievement in this area, and still a lot of things you saw that we need to work very hard to achieve, and ultimately all of your achievement, all of your hard work in the future, it will help our society in this part of the world and also rest of the world. Everyone will be benefited from there. So your knowledge is very vital, your hard work, your commitment is very vital, and I always think that you should attend any of this opportunity in the future wherever you have. Please do not neglect, because you will find opportunity to learn a lot of new things, and that will help you a lot. Even I am sitting in this room, I also learned a lot of things, and we are collectively learning. Nobody is that we are absolutely knowledgeable. All the time we are learning. Our learning curve will stop when we die, and you know that every one of us, as we are born, one day will die. So our knowledge will not. And again, another important thing, your knowledge does not need graveyard. You need to share your knowledge with other people, and that is the vital thing. So therefore I thank you all on behalf of my colleagues and the organizing committee, and also the government of India, because they actually helped us to make this happen. So, and also of course the host institution, the Motilal Nerhu National Institute of Technology. And with this note I want to stop, but before I stop I wanted to share one small thing with you, because I was thinking on the other day, I was talking about, even today Professor Roy mentioned about Ahmed body, and some of you are already familiar with the Ahmed body, which is a standard body. His full name is Syed R. Ahmed. He is from this part of this world, particularly from India, and he spent most of his time in Germany, in University of Brunswick, and his very close colleague was Wolf Heinrich Hucho, who wrote a book called Vehicle Aerodynamics, and this is a Bible. Those who are doing the Vehicle Aerodynamics course or do the research, they usually. I get an opportunity to meet him in 2001, exactly 22 years 6 months before, in February, in Detroit, the Kobo Center, in SAE World Congress, SAE Society of Automotive Engineers, and I remember at that time it was around 10,000 people. So it is, I never saw any conference such a large scale. I think 8,000 people, and some people say 10,000, but there are the two arguments, but it doesn't matter. It's a big conference. So Syed Ahmed, he traveled from Germany to Detroit. And our session, because there are a lot of sessions, as you know, the 8,000 people are the various aspects of the automobile, so they had a lot of parallel session, a lot. Only people, those who are going to a particular session, they are focusing on that. Still they couldn't cover everything. So Syed Ahmed, he came, and his luggage was unfortunately did not come at the same time as he came. So his PowerPoint, not PowerPoint presentation, the overhead projector, there you have a special slide or a sort of transparency. It was, of course, in his bag, and he realized when he landed in Detroit. And then what he did overnight, he wrote some of the important things that he will be talking in a piece of paper. And then this paper, that with this he came. And of course he apologized to every one of us in the participants that things happened. And then, but he is a little bit old man. So there is a lot of page he wrote, and there was not a page number, but so his sequence can go easily wrong. So I am the lucky man. I told him that Professor Ahmed, I can volunteer you. So I can, you stay there me, and you put the sequence, and then when you finish one particular page, you tell me, and immediately I'll put the next one, and I'll keep the sequence, so that you will not have any, because he already has a tension, because everything is lost. What are the things he wanted to say? Not everything he could manage, and that was the important moment in my life. And with this note, thank you.
Now the organizing team would like to felicitate Professor Arnab. So may I request Dr. Abhishek to please present Professor Arnab a memento. Dwarkesh, please. Please come close. Yes. Professor Firoz, please come. Please join with us. Now I request Professor Firoz to please present another memento to Professor Arnab.
This one? No, that one.
This is the direction.
Yes, wrong way.
Hey, after asking, please, John. Good. Thank you. So, with this we conclude the session for today. Tomorrow, all the participants, even one or two participants who left early, I request all of them to please come by 8:30, because after some preliminary discussion with Professor Firoz, because Professor Firoz will leave tomorrow early, so we'll start our evaluation process at 9. The evaluation is mostly MCQ based or fill in the blanks based, and tomorrow in 1 hour I will upload the lecture of Professor Arnab to all of you, and my advice to you is please go through the PowerPoints what organizations have circulated to your WhatsApp group. Your evaluation process will be based on this PowerPoint mostly. Okay. So tomorrow please come at 8:30, and the certificate distribution ceremony will be around 10:30. So unfortunately, we don't have, we're not having these two experts tomorrow during certificate distribution ceremony, but our head of department and local GIAN coordinator, Professor Sahu, will be there. Okay. So tomorrow, don't miss, don't come late. Please come by 8:30 in the morning. Okay. Thank you.
All right. Thank you. Have a nice time.